a little bit of material science. You're not going to be experts in this, obviously. It's one lecture. But the issue is, as designers, there's lots of physics and things that creep up through the stack that you have to then address when you do design. And you have to actually change your design in order to accommodate for some of these issues. And so it's more of a, oh yeah, this is the cause of why I have to do X. Okay.
Right.
And
welcome back, everybody.
Pretty
I'm going to get started.
It also applies.
I apologize. I ran over
how
last time.
why chips are cheap.
I ended up going about 4 or 5 minutes over.
So
I'm going to step back and kind of review a little bit of stuff. I know some people stepped out.
Remember
Before
the
we stopped at
syllabus quizzes
class.
in Canvas.
So I
Please
want
do
to
it
make
at the
sure
end of the week,
it's
otherwise we're
you
the
guys
class. To make room for some people.
Basically today, we're going to talk about finish this up. There's only credit or not.
And then this, again, you join the Slack channel, which is where all future announcements are made in the announcements channel.
And then we're going to start talking
only
about
I
the
or TA can post in the announcements channel, but you can follow up with
cell
questions,
libraries, which
or
is
there's a
stuff you
separate
know
questions
channel.
channel. This way you have to read the announcements channel for information. So
in terms of announcements, we're also going to release homework 3
stuff I put up,
which will be due in another week.
Pretty low volume.
I will say I think homework 3 is harder.
That's generally how we're going to run the class.
Homework 2.
Oh, I should also say I also put homework 1 on mine.
It's due on, but
TA
TA can help you with that.
But again, went over the grading policy and all that logistics
last time.
stuff,
Majority of
so
what
there's
challenges was
homework
homework 2.
2.
But if you go back and kind of do some more demo stuff,
the one key thing that's in the instructions and on the
things should be much clearer.
assignment itself, put your answers in the space
Any other
provided.
logistical
Do not attach extra
besides
sheets. Do not write it all on separate sheets. We're gonna, if you want the same things, we're gonna use GradeScope or something, grade it. So, I mean, and again, the grading is just did you do it or not.
Right.
There's no question. We'll post the solutions basically on the due date, so you can see everything. All right. That all good? So, I'm going to told you I'm going to read the slides. I'm going to talk about that today in the demo. Okay. I'm going to try to phrase it in different ways.
And also pay attention to the questions channel in the Slack. I know a couple people dropped off Slack as inactive users. That means you haven't logged in.
The only way you can do well in this class, or the way to do well,
answers are likely answered there.
And
questions are likely answered
again, you need to kind of look at the problems.
Don't email
look
us
at my lecture slides and process the information to be able to do the problem. I provide you with all of the information.
Okay, so we're talking about resistance originally with devices and transistors. Then we started talking about another component of delay, which is capacitance.
You shouldn't have to
ask your friend. Then you end up with these charging and discharging capacitors.
If you get stuck, it's then going to identify gaps that you didn't understand.
This is kind of the summary of the capacitors that happen when you have. Basically, this is a single inverter.
Some will be
over here on
homework.
the left side here,
test you on the same idea,
and it's driving another single inverter over here on the right.
I can't evaluate what you know the material by giving you a different problem.
The capacitances that affect the delay
I want
of
you
the
to
first
think,
inverter
not
can be basically lumped together into a single capacitor called CL, which we use for simulation or delay lookup, which we'll talk about later, and so on. It's shown on the bottom. Now, which capacitors are these? Well, if you look at the different components of capacitance, this capacitor right here is basically the base capacitance of the P and NMOS of the inverter.
You have to try to predict what
contribute to the delay of that inverter itself. It contributes to the delay of the previous stage that would be driving that inverter.
Test certain things.
So that's not included.
So you know that I'm going to
the gate capacitances of the fan out. That's what I think about. And you can see, so this is not
educator. We want to evaluate.
You can see the gate capacitances over here are included.
And those core topics are going to component for different problems.
PMOS and NMOS. And
that's the reason
last time. There's 2 components to this.
We're in an era of AI and
overall gate
capacitance.
capacitance overlap with the source drain.
Right?
It was represented as CG.
This is an area where it makes.
Now you may say, okay,
mistakes that
it's
sound
connected to the
plausible,
gate,
but not right.
obviously. But then
if you rely on that,
PMOS one is
can make it
connected
better in the
to
future?
the supply
Maybe not.
VDD and
but by recalling stuff, it also helps you kind of conceive of why is that possible. And
basically because the body of the transistor, so the PMOS is going to be in the substrate, whereas the PMOS is going to be in the well.
In the era of AI,
and those are basically connected to the side blocks. That's why they're connected there.
However,
However, when you do approximations in a different way, you'll frequently say, "Oh, I'm not going to connect this to here." So we're going to actually approximate it to ground. But
try the problems, do them on your own.
This wire capacitance here is also from.
Today's lecture, we're going to talk about semiconductor material types
here on the
what is a semiconductor and so on,
which are due to the source and drain
capacitance
capacitance of PMOS and
the capstone class. I talked about
those are the self-loading
capacitance.
capacitance.
Interposer design, like 2.5D.
That's primarily due to the drain capacitance, due to the diffusion region between
we're
the P
talking
and
about the
N
basic steps of semiconductor
It depends a little. It's a
processing,
diode, but it's an off
Explain
diode.
what it is.
It's actually usually reverse or unbiased.
Chemical
It
steps
has that diffusion which has a capacitance across it.
And material steps.
And those come out as this capacitance. That's why it's between the drain here and the body here. The drain here and the body here.
Stacks of metal is
again because those bodies are in the well essentially or the substrate.
So
now
again
for these, we're generally going to disconnect this from the body and just say, oh, it's the ground.
On the
And this is just the
process
ground.
that you'll use in this class.
So why would you do that? Well, now you have all these parallel capacitors with one side
looking into the
they're
all
all
pass
around.
around.
And they're all connected to the other side.
You're going to have a chip that's running
sum those up
to
and give you this
side of
capacitance
CL.
CL.
So a lot of 3D visuals.
So all of those equally contribute to the delay.
And what you're going to see here is
and so now
in the bottom area down here
contribute to the delay.
These are basically your
capacitors,
capacitors,
interconnect capacitance, and the fan-out capacitance.
And this is frequently called the
together they have equal
front end design part of a design.
Which one do you think
terminally means nothing to you now. But then you also have this giant stack of
trick question. Maybe fan-out
here, where each of these
fan-out
things
might dominate if you have a lot of fan-out. In this case, one fan-out.
This is frequently called the background line. But the other question is how long is the wire? I don't even know why they call it that.
I don't tell you.
But
on the
bottom, the very bottom, you're going to have
silicon. If the wire is very short,
in terms of these
almost
transistors.
negligible.
This material is called polysilicon. Ballpark what this is. And then you see this gray stuff is basically
sizes away.
The hole through the layer.
Start getting more than that.
One bottom layer
to have a long layer, and the delay will actually be more.
These are called
capacitance be more significant.
and they're connected between each metal.
But
So in this picture, all the metal is connected.
You have a fan out of
every layer of metal
16 that can
dominate
dominate
the layer above it and below
for
with that single V in the middle.
So
now,
yeah, it's a little bit
you can see that
I'm going to have an entire lecture on interconnect capacitance
because the rest of them are labeled
in modern
1, 2, 3,
designs,
4,
if unchecked, interconnect delays will end up dominating.
Similarly, the V's are named. This one's named Lycon and MCon, but the rest are named 1, 2, 3.
I started to step through some of these and just kind of ballparking the self-loading capacitance.
It's very similar in ways to
detail,
PC boards.
but the point of it is how it scales with the size of your
phone, your computer.
You can see with a single NMOS down here, you have self-loading capacitance due to this drain.
You don't have the active layer.
You also have some capacitance here due to this source, but this doesn't really matter that much because it's in the ground net, and that's not switching, so it's never going to have a delay associated.
Another slight difference in
same thing with the pull-up PMOS. You're going to have some capacitor with the source here.
In this case,
but we also use one.
Only connects between metal 1 and metal 2.
And then you're going to have a capacitor here.
And whereas in a PC board, often NVIDIA will go through all the layers.
Based on the sizes,
through the PC
we
board,
draw the layout
metal
of that
line
PMOS. It's going to have a width that's twice the NMOS.
Whereas here,
and that means
I
it's
can
going
say
to end up having a drain
through this
area, not perimeter that's roughly twice as big as the
not have
NMOS.
So it's kind of
we kind of
disconnections.
I'll talk about that later back today. I don't know.
But this is basically a side view of this, and this is interesting because it actually shows you
we
the
draw
dimensions of all the layers.
a single transistor in the pull down here.
Diagram
Say
has
this is the size of one.
labeled with some
that drain capacitance is proportional to the area of this, as well as the perimeter of this around here. Two components. But then if I have a PMOS, and I draw this as roughly twice the size.
You notice it's in layers, kind of from a silicon substrate, which is the bottom part, all the way up
I
to
didn't really
the
do it super proportionally, but this has roughly
This is
twice
like
the
a
area.
cartoonish version of that
And
same thing. This
at least has
like an
double
old drawing,
the
but it's
perimeter in this
used in a lot of
dimension, but
textbooks.
this dimension actually stays the same.
And I'll make a side note here. You notice
why
it
it's not
doesn't
quite
require
double
a
the
textbook for the
almost
class, but I have several two optional ones.
Self-loading
They're very
goes
old.
up as the transistors get bigger.
There have not been any
In addition,
better textbooks made.
self-loading will go up as you have more transistors
a lot of the
connected
stuff
in
is
different logic functions. You see on the left,
don't want to
the next
divulge
gate build a
the
NAND
so
gate.
they're not going to write a textbook.
Here,
know how we
you
make
have a
chips,
drain
because they'll help
capacitor
your
in the middle.
competitor make the chips.
For
The second
B
reason is professors
gate.
don't make money
So
selling
now the
books,
source
they sell
capacitor of
how many
the
people are
A
in
transistor
design
does
not
that.
enough to make books.
It's not connected to,
And a
it's
lot of
not on the
people
ground
don't.
net like the bottom transistor
You can
anymore.
probably
So
find
that
books
internal
online, we
capacitance
have
between the
them
A and the
for
B
that, but they might
can
be
come into
available
play.
somewhere.
That can add to the delay of the gate.
They're also available in the library for free.
In addition, you're going to have all these
Old
capacitors
school
on the
higher
output
books,
net.
so
You're going to have
you
this
can look at
source
it.
capacitor here,
And you
and
can
each of these
copies
parallel
them.
transistors is also going to have a capacitor.
Yeah, so
And all
this
this
is a little
will
cartoon
add
diagram of
output,
that.
so that's
It's called a
self-loading
dual
capacitance.
well. The reason I'm showing
And
this
then
is
the two on the
mostly
top
the
matter because
bottom
of the
layers,
display.
where you can see that there's a
So
lot
you
going on.
you have parallel transistors on the output, they sum up,
You
and
have different stereotypes. We're going to call these like
Now, if you look at the NOR on the right,
We're
we
gonna
talk
call
about
this
the sizing to
N-type,
make
and
the
then tell you
delay
what these are in a
equivalent to
minute.
an
So they're
inverter.
all
You know,
silicon.
in this case, we're sizing up the
Figuring
PMOS
out
for two
how
reasons.
tight
One,
the silicon is.
because the
It
PMOS
changes
is reversing
behavior
the
what happens with the devices in the
But then you also have to
silicon
make them twice as
by
big because you have two of them in
changing
series.
You
And
can
that
change
makes
the size
resistance
not only
double.
when we
So you wanna
manufacture,
counteract
we
that.
actually
That's why you
change
need
it
the
based
4x
on electrical voltages
polarity.
applied to it. That's why I call this
Also, when you have the 4x,
silicon,
though,
right?
they then have roughly 4 times the source drain capacitance.
Materials and the
So that internal capacitance here,
which is pretty cool. It's a unique thing.
There's actually going to be much bigger. I'm drawing just one capacitor.
Silicon is the
Then
most common one.
the NAND pull down.
But you can also use gallium arsenide.
And then the point being, as these start scaling up, I'm just going to gloss over these.
Boron and
You know,
arsenic.
this is 3 input NAND, 3 input NOR. It gets
different
worse
types of
types.
semiconductors.
This is why I mentioned you don't generally have cells
I don't
more than
want
like 3 or 4
much
inputs
more
on most
into
transistors.
No.
So once you get
How
that
do we
big,
manufacture this stuff?
well, the inputs, you end up having
starts as
really big
silicon.
PMOS devices.
Same
They get area inefficient.
purify
You
sand
have all these
into
capacitors
silicon,
associated with them too, so they're also
It
slow.
is an element.
And so you're going to
It gets
instead do
made
logic
into a-
restructuring, where the
it
EDA
basically
gets
melted
break it
down
down into,
it's
say,
put in as basically
2
a
levels
seed
of
crystal
NOR
of
gates.
silicon, and then they kind of draw it out into these little things called silicon ingots. Right?
So
These
it's
things
much more efficient
can
to
be
do
anywhere
that
from about 8 inches
So
around to
I'll leave that here, but you can
anywhere
kind of see the
from
general
14
trend.
inches in diameter.
Now,
It's like a big fat.
and then switch now to cell libraries. So that was the end of the lecture.
Okay. And what they do is then that's a bad analogy, but then they basically
This is where it starts to get a little more interesting because it's rather than kind of theory behind things, it's
which is shown on the upper side right there.
it's stuff you actually see
Wait for you
in
to
as a
notice
designer.
there's actually one side that's beveled, that's flat, because you want to know the rotation of the
Like,
wafer
you
during
might think the
the
electrical stuff that when you
get
simulate or
circle,
you
you know
measure
which way
performance,
it's
you might have an effect, but you don't generally have a direct
then
control over
notice 18 inches
resistance. You know, you can kind of analyze
on
it.
the right here,
Other
you
tools
basically see a
can
bunch
do
of
that.
dies.
Cell libraries are
There's
another issue.
chips on a single wafer.
Now,
you notice here
again,
how they basically
do your homework. Okay.
dice it
Homework
up.
due on
they
Sunday.
cut, they saw it
Please ask
literally
questions. We're happy to ask
into,
questions.
rectangular
Again,
shapes, which are then
once you try it, and if you get stuck, you
and
can
you
ask
can see a few
questions.
guys here that
Of course,
correspond to
help
places in here.
But what I don't want to have is
Notice on the
spoilers and
edges,
have people not try
there
the
may be
homework before
incomplete
seeing
dies
this.
along the edge, so
So
you have to have
don't
a full
go
chip
through
to have
the
a
question form and look at all the solutions before you try it.
Actually, I brought
Beg you
a wafer.
to not do that because
This is an
that's how you
8-inch
can do well on
wafer.
the exams.
I actually bought it online. It's not my design. You can buy them on AliExpress. You can get a 6-inch
I'm
one
preparing
for
an exam
20
now,
bucks.
midterm.
I think this one was about
There's
30
going to be
bucks.
5 or 6
The
questions.
18-inch ones get up to like 70 or 80
What I'm going to do
bucks.
is some of them are
But
going to be
this
very
is-
similar to the
from
homework.
what I can tell,
Different numbers. I'm not
it
going
got
to
shipped direct from China, right? But
similar.
It's a design that
I think one of them is
tested
going
for a
to be
fact.
a little different.
So there's a
The
design
other
on
is going to
there.
be quite different.
It looks like a bunch of test patterns
So
of
this is
different
going to
layers
test,
process.
you know, did you do the
Homework
homework
basically like how do we
geometry
make money off of our garbage?
but not
send them to people.
The next one's going to be like, can you do kind of minor
I'm gonna pass
applications
it around,
of
people
this
kind of take a look at it and so on.
And the next one is, can you apply the things you learned to a new
I have no
problem
idea what
using the same
technology that
system?
is. I don't really know what design it is. Just kind of my guess. Because usually you can't buy those. You basically get them as dice
Yeah, I
wafers
don't
from the
like memory-based exams. I don't want you to
Now-
regurgitate. I will let you use a sheet of paper
And usually
on both
this
sides.
is
You have
silicon
and
or a single, what's called P-type.
I don't care about
We'll get to that in a second here. Yeah, question back there.
Not typed, not printed. Otherwise, I get people taking homework, zooming it down, and putting it on an 8.5 by 11.
Oh, why did they
You
print?
can't take my
That's a good
solutions
question. Why did they do it there? I don't know.
print
This
them
one doesn't have the
That's
ones
not
around the perimeter printed.
Someone did that
I'm
last
not
time.
sure
Maybe
what
that's
they did.
they're kind of angry,
You're right.
but I'm like, I was explicit about this. You can't do that. But okay, you know, and I think that exam's fair, right?
So,
I think that's my
what I
general
mean by
approach,
N-type
and
and
that's how you should focus your effort studying.
How many of you- has anyone
And you can see
taken
there's other two
introduction?
problems, which
No.
2 or 3. That's the
This
ballpark.
is
I haven't made
one of
it.
those prereqs where
To get those is what you really have to
curriculum
understand
changes
in 3 or 4
I was a
years to do
computer
this
engineer in
process.
undergrad.
Yeah.
I had to take computer inorganic chemistry. I actually took a class in processing, but now complexity is so much.
Everything I
all
cover in
over
class will
the
be
place,
I'm not going to have any more questions
you
about
guys
the
are learning more about
Okay. Everything in class, everything in the
more
assignments,
machine learning
everything in the
stuff,
homeworks, they're all in
in
the
the spectrum, there's more details.
No more questions
So
about the exam.
basically, if you look at the periodic table, I like the point there, but it's also easier to do this.
I'll give you a hint. The homeworks are
You
whole
look at
exam
the periodic table where
questions.
you have all the elements here,
Okay.
and
Every
every
time I
time
come
you
up with
can see
more
silicon
questions,
in this
I pick
element
the
right
best
here.
ones. I pick a range of questions.
And it's
I don't
about
necessarily have full
14
questions
of
because I have to take
periodic
class
table.
all the time.
And
So some of my
what
old
this
exams,
means is,
I don't ask questions like that.
I'm not going to get into too many
But
details, but
you'll get an idea
it ends
from
up having 4 electrons.
that's
It has shells around
Okay,
it. the
let's keep going for
nucleus
this.
of
So,
the atom.
cell library
Whereas
stuff. This is
the outer shell has 4
this is kind of
electrons, which is half
interesting.
of the 8
This is actually what got me
electrons
into
of
this.
the
I'll tell you this. When I went to IBM, my
Yeah,
first
I do it
internship,
in rows,
they
like
some
all
hallway they ran an internship at IBM. Yeah, question. But yeah, back there. I went there and they actually had me doing design, and they were like, I was on one of their processors, not power processor, but the AS400 chip.
Not really.
And they had my component design was the L1 cache bypass. So if you had a cache miss, you put a memory, it would skip the cache
case,
and load it directly from memory. Tiny part.
this is
And they were
phosphorus
experimenting
from
with a new kind of technique.
I can't even see it very
And I had
well,
taken basically a layout class.
And then the
where
other one we use is
you draw
boron.
you draw the polygons and stuff like that. This is how we used to teach the class. But their
actually
project they had
here.
me was there was a research group at IBM in Haifa, Israel.
These end up
came
being
there.
used.
They had
They're
a
very
program
similar
generated
to
layout
Silicon,
standard cells.
except
you
one
go
of
to
them
Spice
has
Atlas
one
and the
extra
technology
electron
parameter
on the shell,
it would
5.
generate
The other
say
has
this layout automatically.
And you may say, okay,
It
well,
was a little bit less
massive
efficient than doing it by hand.
The
The
N type
50%.
has the extra electrons, and that
Their
ends up
question to me
being
was, this was a design,
providing an
this
extra
is
electron
not
charge.
necessarily
The other one ends up accepting
the product we're applying it. They had a question.
situations.
Well, we have a
Well,
library of cells that we have for our design that we do
Well, the
synthesis
situation is
with.
that it
Or we
forms
make
a lattice
library
like
specifically
this,
for this.
So it allows you to do 4 cardinal
the
directions
control cells
and
and the
basically,
muxes and so
if you
on.
have pure
inside
silicon, it'll form a
how
bond
much better would that be
for the
versus
directions.
just synthesizing it
And
and placing around?
since there's 4
Or do it by
electrons and
hand.
4
It takes a long
vacancies,
time.
it fills
So
up
I
the
kind of
shell
compared
with
this
the shell
methodology. I don't remember what the
This forms a
conclusion
perfect
was. It was a little
lattice.
inclusive. Probably because I knew and didn't know what I was doing, and my results
really
by hand are not good.
Now, if you
But,
introduce these
it got me into
different,
this. We had like,
you
oh,
literally,
all this stuff
they're
is
part of the
CS
solid
problems
material.
doing
So they're
cell
embedded in
building
the solid
problems,
material.
which is fascinating. And I
And
didn't want to
one
use cell
time
layout by
it's
hand when I went into grad
heat
school.
up, it's heat up
Wasn't
and
really
flow,
a job. No one
you
does
introduce
that
these
much because they use
talk about
libraries.
other ways of introducing them too.
It got me kind of infatuated with libraries and like looking at them and how they're designed. And I have a lot of insights into this that are not covered in
extra
books
electron.
and
Suddenly you now have
research
5
papers really and so on.
but only 4 bonds.
That's what I'm trying to
So
summarize
that's
here.
the fifth
This is
one.
not really in any of the
It's kind of
books
like a
that I
cup
have
full of water. If you have like
It
an
just
extra
doesn't
drop of
exist.
water, it's going to flow out of the cup.
Some of it is pretty simple though. Generally,
flow over to
the
this next
libraries
one.
will always have a
Well,
fixed cell height. What I mean by that, we've seen examples
So
of
you have
that.
these extra
And here you can see two different cells, and the distance between the power up on the top and the ground down here is a fixed height.
Carrier is what it's called.
Now, notice this height is actually also to the midpoint of that VDD wire and the midpoint of the ground wire. Because the reason for that is you end up making these rows, and every row is actually going to flip, just being a vertical. And so that VDD is going to be shared with the VDD of another row above it to flip upside down. Why do they do that? Now save the wire. You have one less
I'll
wire
also
for
say
every row. If you have 100,000 rows, that's 100,000 wire
silicon
tracks.
is not the only semiconductor.
So it's much more
The other one is actually germanium.
And you think that this cell on the bottom, I think it's a flip-flop. Usually flip-flops are the biggest cells. It still fits in a single row. But you can see that it's the same height.
You send a chip up
Unless I
space,
zoom
maybe
in
that and
correctly.
not
But
silicon.
this is actually the same as the one above.
So
now, every cell in the
same
library in general
principles
will
to
have
apply.
that
They
fixed
have
height.
some different
Now, what is the height of it?
obviously manufacturing is
You may
similar
have
but
different
different.
versions of libraries with different heights.
So this intrinsic
in general,
carrier moves around.
if it's a dense library, it's
not
going to be
a lot
like
of
7
them.
tracks.
You might say, okay,
by
strategy.
That means you can
You
fit
can.
7 metal one
But it's
wires
not
through the middle
power.
here horizontally in parallel to route in that
What happens when
fashion.
you have solar cells?
So this kind of gives you an idea of the
Solar cells,
probability
you have
in that dimension.
solar energy coming in and doing this.
12
It
tracks are going to be
extracts
much
more
bigger. You're going to get 5 more wires going through.
PV arrays.
But your transistors then might have blank space between the transistors. You have
Don't-
small transistors
you
that
have
don't fill the
another
entire
material,
cell.
also silicon, but
So it's
instead
very
here you have what's called a hole. The hole is an absence of an
Yeah,
electron.
that one's this
It's not
blue
really
region
a
for
particle,
Pauli diffusion.
and
And this
physicists
Li
will
is
kind
this
of
tan.
cringe
So
with that idea of a hole, but electrical engineers call it a particle.
That's the local interconnect. It's still an
It's like a
interconnect.
not a
That's only used within cells.
Literally all of our equations work in electrical engineering.
Whereas you could use metal,
like it's a
say
particle.
metal 1 here to go this
The
way to
idea
connect
is
to another cell
that
later.
the absence of electron moves around.
That's why you want to be able to use metal here without a single here all the way through the cell. There's no obstruction.
Takes one from here, now this one's short.
That's why you want to be able to
Take one down here, now this one's short one. So you can have an absence of
And
electron.
now you can see that the width though this is much wider.
Interestingly enough,
It's very
the electron actually moves faster than the hole.
I forget the actual
Why?
ratios,
Well,
but this is probably like 20,
Like I said, just
15.
electron is actually a particle, and this one you're
fixed height.
basically waiting for this vacancy to fill up. And you
There
only
are
have
some
4
libraries
candidates
now, and this is an example of like as a designer running into issues. Some modern
So
libraries
perfect
are
guys, you can change the material.
height cells.
Now what happens
So
is
instead of having
you add
flip-flop this
lots of
wide,
these dope
the flip-flop is actually going to have
new material
ground,
that changes
VD,
the electrical
and another ground, and that's like 2 rows.
If you do it enough, it becomes a
Or
conductor.
you have the opposite where it's
Both of those actually become
VD,
conductors.
ground, VDD. You need a second implementation with the other one flipped.
But
Otherwise,
you
you
also
have to
do
put it
it
always in the correct pair of
talk about
rows so
that.
that you don't short circuit the VD and ground.
So the wafer, you're talking about printing on the boundary. Well, you generally don't print. You can see an example here, along the perimeter. All these parts.
So
This is a very
why
small
one
chip
VDD,
on
one
a
ground, one
big
VDD,
wafer. Whereas
Yeah.
that previous
It just depends on
chip,
which
there's a lot of wasted space.
which 2 rows you can put in to give you flexibility.
All these kind of vacancies here.
Right, because it has to match the
When they
existing
actually
rows, all the
manufacture this,
other
this is an
cells.
18-inch wafer example.
The nice thing about this approach is you don't melt the
15
VD
millimeter
ground.
chip, which is a pretty big chip. It's a
Yeah,
decent sized chip. How big are kind of the biggest chips?
For 2 layers, what?
Generally, actually, I can't answer this question now. With all the
what connects?
NVIDIA
What do you
chips,
mean,
I don't know the actual size of those, but a lot
Oh,
of
that's a good question. So if you have one on the bottom,
connected
connected
to
to the top, you use this Li layer.
big
And this Li could go through
The reason I don't
but notice in
know
this cell,
is
when you give an Li underneath the power rail,
is
so it's actually blocked all the way
manufacture
across.
this, you're doing it.
And then you have metal 1 all the way
You
across
end up
the power
having
rail as well. So it's kind of
particles in the
dual
air,
stripes to
and
reduce where you
particles
here.
here.
And that's useful when the
What
rows are
happens
really
with dust
long.
particles,
You want to have
and
high
contaminants,
resistance so
but
that
you have
the
a
VD goes down in the
manufacturing
middle of your row. That's
And
another
you see here,
complicated.
this is actually showing.
So in general, what would happen is you would
before
not
they
use Li, and you use
remember,
underneath that.
One's
with
particles,
Li.
one can be discrete differences in the manufacturing and
Or
materials and so on.
technically, if you
Here,
have
this is showing this
poly,
wafer
you can also
diagram,
round
identify
poly.
actually
If you have a
which of
transistor down here, you're going to connect it to a transistor
non-functional
there, you route
dies
the poly
before
here,
you
and then connect them vertically lined.
right? So it's kind of marking the defective dies with this.
So
kind of
that's
gray color.
something to do.
Partial dies are shown.
Now
in
the problem with
yellow.
the 2 height
And then,
cells,
there's no waste.
we're going to talk about placement later in the class. The placement
You
is
then
not my concern.
want to kind of predict
It
how
often causes
have
problems. And that's something as a
multiple
designer we
different
might have to finagle the options in the tool to get it to work right.
Now, there's a
Or
trade-off.
complain to the people
You have
at
a certain
the EA
defect
company, like,
density.
hey, it's not
If
handling
you have a
the
really
library.
tiny die,
Or you want to
the
pick a library
library
that
something
doesn't
not working is going to go down.
right? Because
There's
it's
less
maybe
area
cool
for
for
that to
density of your
happen.
library, but in
Whereas
practice,
if
it
you have a
doesn't
big
work.
area,
Tools use
the odds are you're going to have parts.
So
You
it always
see
kind of
uniformly distributed over the surface.
Yeah, just an example of different height cells. This is actually in
area,
Skywire
likely
and
to
also
work.
for the 127 class school foundries. We have two
Probably
libraries,
less
multiple
stuff.
libraries with different heights.
So
This one's
that's why
called
I'm kind of letting you know
HD.
that the biggest
There's another one.
guys tend
I
to
forget
send
what
here by
it's called.
saying
7 track,
there's
12
a
track,
trade-off
15
of
track.
how many will work versus how much you can fit
I
out.
might have actually just scratched the image just for effect. These might be the same layouts. I don't remember. Because yeah, there are some differences. You're right. Yeah, but you won't always see that the transistors in this top one. They won't always occupy this full region. Like you could have some blank space here if you have small transistors.
I grabbed this image from somewhere else.
And that's one thing that this doesn't.
270 by 470
So
range,
that kind of, which is making it too tall, kind of waste area.
You know
where
why
you
they
can
can probably do that? Well, they play tricks.
One thing they commonly do is
you think of
they might have a different library depending on what you're
there's
making.
a lot of logic.
For example, if you have a lot of complex control logic that's doing decisions
What
stuff,
happens if you have a defect?
you might use a dense library.
Exactly.
If you're making something like an ALU,
So you might
where
have
math functions and stuff,
540
you have
processors, but
like
as
a
long as
register file or
512
like
we can ship it
passing
away.
buses through at a low metal layer.
That's
You might use something like that.
redundancy and
But
data
data paths
paths
down into
dynamically
like a higher track,
based on what
higher
works.
height cell.
Same thing with multi-core processors. You can actually buy a 3-core processor. What is it?
Yeah, you can have different
Four
blocks. So just like you can make your ALU and like
part
part of it, the one on the right,
you
you
know,
can make your
low
control
end
module with one.
laptop from on discount.
Depending on how much you want to spend on kind of optimizing.
Most people don't need 4 cores.
Other
so
designers
it's
might just say it doesn't matter that much. I'm just going to synthesize everything with one left.
Yeah, that's exactly why.
So, but it could have a difference. And that's an example of something you have to kind of do manually. The two tools don't trade that off for you. So
that's
they
a
don't
good
generally
question.
mix different row
Is there
heights
a
in the
pattern to
same
this?
block.
There can be.
Like the entire block will generally
There's kind of a whole field of the. It depends what's the cause of the defects. So if it's dust particles, it's
Now we
probably
have a look at different logic functions. We've seen
later
inverters already.
processing steps,
The
there
right
can be
example
certain
of
steps that are systematic.
Man 3.
Like
These are all in Skyless 30.
There's going to be one step later where you basically spin a material onto the wafer.
Part of your
You
homework
can
is look at a couple of these and kind of go through the layout and see what they are. So I'm not going to dig too much into
That'd be like
this.
the photoresist
I already talked a little bit about that.
So depending on what causes the failure, you can have different things.
You can have more complex functions, though. We talked mostly about NAND nor inverter.
A lot of times when you
also
make a
have
die,
buffers, but
you
you have complex states like
this,
this,
there's actually space
they're
between
usually
dies to
encoded
be able to
and they're naming in a
cut
similar
through
way in different
chips.
libraries.
You have space
convention that's
What they'll
normal
actually do is put test structures between
so
the
if you have
dies
something like an
that they saw
A21 OI that's an
and
ALU
use those to test where
inverter.
things are good.
The numbers say
Now,
how many
what
are
are
AND together
test
and how many
They'll
are
be
more.
very simple
So
things.
two of them are
like
AND
an
together
amplifier
and it's
or
OR
an
with one
oscillator that
input,
runs at a
and then
frequency or
output
something like
inverter.
that. And they can measure it and say,
Or you might have one
does this oscillator
for example,
in this area run
A21
1 gigahertz? Like it
That
should.
would
And
know
that's
that
not
that's probably what it means. You would tack an inverter on this because this is an inverting logic formation. You would uninvert this output. This is actually why bar. By convention, the SkyWater library labels all inverted outputs Y.
Oh, the wafer
and
limit is
uninverted
just the edge of the
outputs
wafer.
X.
No, on the
That
edge,
just
you're
has
gonna
to be for
see
the
it's not
SkyWater.
perfectly
That's not really consistent.
flat on the edge, right? There's going to be kind of a bevel
But then
edge
it might label the
to prevent
inputs.
it from flaking off.
It might label them like
They
ABC
label
for the inputs.
it's very fragile.
Or it might say
They
like
can
A1,
break.
A2.
And so they
then
bevel
B
the edges so they
over
don't crack and
That's another
fracture.
kind of common naming scheme, like on the top
And,
there.
they actually don't carry
That
around
differs
individually
though
usually. They're actually
between
using a carrier. It's a box, like a
So,
lunchbox
you see,
size thing.
like,
and
why would
they
you wanna
carry
use a logic
like
function like this?
a couple dozen wafers at once. They carry this thing around like a cartridge and put it in the different processing machines. Yeah. No, generally the partial die is unused. That's a good question. It's missing
Oh, the O is
half of your
output.
circuitry.
So it's not saying you're done with the numbers.
It may have half an inverter.
I don't know if it's actually like a
Inverter we cut
formal
in half. I don't know.
language. Someone named it. I don't know if you can come up with like a regex to parse them. You probably could. But you'll see things like A2221. It's like just a bunch of ands in an org. Now, why would you want to use things like this? In terms of me understanding what this
I guess
function
you
does, it's
could
not
try to
that
make
useful.
a design such that
it could be used by the synthesis tool.
a
This
core that
could be used
touches
for
the
taking
number
up
of generally the number of the
Instead of
ones
actually
that
using
are so few that they
that
ignore the
and
loss.
with the or the B could like disable
Talk
the
about
outputs
why.
and force
Often
it to
when
one.
talk about
So it can do
packaging,
something
it's
else.
usually very important stuff on the perimeter
So
of the die.
it can be used for
So
like
you can't
logical
have half
implementation
of
boxes
it.
or
Won't work.
you're generally not going to do standard two-level sum of product or product of sum. You end up with like multi-level deep
Yeah, so
logic.
the lines
So this
between
function could
the
be
die are
used
called the
depending
scribe
on
lines. That's what
function
test
you're
structures are, and so on. Now, here's actually a SkyWater wafer.
In addition to the different functions being
I
complex
actually
functions, you also have
have
different
chips here.
sizes. So this is the electrical size.
I'm gonna pass this one around. This is a single die.
You've seen in inverter one. You might
I
also
don't have
have
it
an
highlighted,
inverter
but
8x.
this is what's
So this is
actually
one all the
mounted
PMOS are
on the
8x
PCB.
bigger, and the NMOS are
chip
1x
to board
bigger.
mounted.
Except how do they actually implement it in
Design.
SkyWater?
So it's the silicon
SkyWater,
is
because this is
actually
the
flipped
short
soldered
library,
directly to the PCB.
you don't have a lot of row height. What they end up doing is doing
This is
different
coming
fingers of transistors.
This
Why
is
they call
a
it
very
fingers?
low-cost way of doing this.
Well, if you look at this,
in a
you
lot
can
of
see that the
things,
supply
like
kind of goes down like
bacteria
this.
and so on. But this, what we're showing right here is actually
And then the
one
poly
of
goes
those
up like
labs
this.
somewhere.
So it's kind of like you're going like this.
So this is the same
Right,
run.
your fingers and transistor every
not
one.
that wafer. One of the
And
wafers
they go together to
is
form
the
that.
process.
So you break
And this
all
is
these
my
ends up being
design
parallel
that I
connected. Every one of these fingers is kind of in parallel. So you basically make it 8x.
So
So
that's a very good
in this case,
question.
it's actually
In this
8 copies of this.
This actually had
Not all libraries are like
designs.
that. For example, if I have a tall track library,
different.
I might just make a
tile
tile
of some
8x
size,
transistor,
it is.
or I might make two of them.
Has
Reduce the
40
capacitance inside.
it's 3 by 5.
Breaking into two could reduce the capacitance.
Whatever that multiplies out to.
But if you break it into two, it makes it wider,
Something
and that waste space.
I'll show. I don't have the full.
I've not seen
design,
it,
but
but you could potentially have a library with, say,
You can see
your
there's
tall
another
library could have
pattern
one
here
that's
that one of these things is
wide
different.
with
This
a
is
lot of
called
fingers for an 8x,
multi-object
and the
wafer.
8x is narrow with a fault
40 different people.
The tools could pick that because they have a different
They
electrical
put them
behavior,
together
same
on one Uber design, some
functional
big design,
behavior.
which they then
Again, I've
made
not seen
masks
this,
and went
but
through the
it's
manufacturing
very
process. And then when they chopped it up, they sorted
Yeah,
them.
so
and
that's
gave
the
everyone
drive strength.
We all shared
Again,
the cost.
this is just the fingering is using kind of these parallel transistors,
Right.
right? So this is showing just two fingers of the poly kind of together. And then again, that was to reduce
I'll
for
talk
two
about
things. It
process
reduces the height, but then it also reduces the
This
cap.
is a SkyWater 130. This is actually the fab.
Right.
This
So
is
this could
actually
be a good layout
right
because it
here.
reduces that cap.
And I'm back over. I forget where I am. I'm thinking over here.
Now,
No, I
remember
did not
gate sizing
manufacture
though?
it.
We just talked about the internal
So
self-loading
it was at
cap.
the plant and with Google and a
It's
bunch
not
of
always
other
beneficial to make
packaging
bigger
people.
gates.
And
Bigger
this is
sizes.
when they open
There's a
sourced
limit
the
because after you get to some
technology,
point,
and we talked about
self-loading
collaboration
dominates and it makes no sense to make it bigger.
When you go into a fab,
So
big
the
fab
biggest
where
gates
bunny
I've
suit,
seen in
you go
libraries
through-
are sometimes
you go
like
into a building
32x
or
or
somewhere,
maybe
they have that room where it's kind of like blowing
Beyond
air to
that,
keep the cold out.
you don't have-
go through one of those, it basically
Absolutely.
scrubs off
Bigger than
dust particles.
And those are
Then
typically
you
for
funny
special
suits.
purposes.
You
They'll
have
be
to
like
cover your
custom
mouth
power
and stuff. You don't breathe out.
Because
This
your
is not
clock will have a
necessarily
big fan out of
using
things
the chips,
and
it's
all over the
chips
chips.
from you, right?
Those will also be
It's a little
special designed
bit
because
technical in
they'll
there.
pay extra attention to the rising and falling delays to
And
match
those
them
defects will
exactly
cause
equally.
problems. So
Because you don't want to have
in
your
this
clock have a
fab,
fast
you're gonna
rise
have
and a slow
different
fall.
areas
Because that
of
goes
different
super
defect densities.
Whereas a
Here's
regular
a wafer,
inverter
it might
could
be
have a little bit slower rise
that
and
means
make
there's
the
10,000
CMOS a little smaller
defects
than
per cubic foot or
smaller
so.
than kind of
Defects of a certain size, like half a micron,
just to
per
save
cubic
power
foot.
area.
How much dust is in the air? Well, if you need to do something that's more accurate,
There
they're
tends to
putting
be
like a chemical
kind of
hood,
categories,
like
and it might not be politically
or
correct.
you may be
I
in
call
like
it
an
short
enclosed
fat
thing like this.
policy.
It might be a class 100.
What
What do they have?
we
They
like
have
all the
filtration
kinds, right?
systems
So that's good.
filtering air out of that to remove particles.
And in
So you
terms of
do
this,
certain steps kind of
they both have their
controlled area.
they're both
Make sure it's
the fat libraries tend to have a lot of different logic functions. But they have a lot of stack transistors.
When Intel came out in the
but they tend to
90s, they did their first Pentium and
But they're
stuff.
more area
Their
efficient.
advertising campaign
You
had
package a
basically
complex
people
function
wanted to
into
do
this
this
area.
expansion.
It might be bigger, but you have a lot more.
And I think
you
most
can overlap
companies
in your
didn't
area.
realize that was like
The
a
polys are
space.
connecting things
It
up.
looks kind of
That
like
local
space.
routing is much more
But
efficient.
they're actually supposed to be fab workers.
But
Manufacturing
it can be
chips.
slower.
And,
You could
they also
have
gave these out
all
as a
libraries.
design.
So this is where you have say, a few functions, but you have a lot of electrical sizes.
Actually, coincidentally, too,
When I was in school,
this is actually
we
made
have
up
like
Pentium.
30 different
I
sizes of an inverter.
1991.
So
I'm not going to pass
so
this.
that's good because then you can pick the exact right size for driving whatever load, rather than
I'll take
bouncing up or
photograph
down to
of
the
it.
next closest.
They did this as a thing because, again, a lot of guys don't work.
Usually the
Trade-offs
trade-offs,
one
and
didn't work.
usually
Like,
the
we
common
do
sweet
this.
spot
We
is
do
kind of
souvenirs.
3 or 4 input CMOS gates, most different options. And
should
about
carry that
12
one.
sizes of inverters, maybe 16. While the other gates usually have like 3 or 4 sizes.
Are there any
Why is that? Well,
cases?
you have the complex gates to
If
make
you go
complex
into-
functions.
let's
Let's
say
say
in
more
courtyard,
sizes so that when you want to
and you go
size
into
something
jack
accurately,
casting,
you add
you
inverter
have
after
to
gate,
right.
you pick the right inverter for the drive.
There's a room, like like 1 or 2
Right,
doors
so you
down,
kind of
and
have to
yellow,
make the best of both worlds.
that's a cleaner.
Now, why would you say that
It's not a super
might you
clean
not
room,
want
like
to
they do
say,
kind
well,
of
all the sizes?
big
Make
mountains
everything have
stuff,
12
so pretty
sizes.
big feature
Make
things.
every
It's
possible
not-
function.
it has
Why do you
some
think you don't want to do that?
They also have different lighting
Yeah.
there. They're not.
These
These
libraries
some of the full lithography
they're big
stuff
files.
they might do.
Yeah,
Yeah,
you have to
design,
design
actually peek in there. There's
Because when you have
window
lots of
can see
cells,
there.
you end up not using them all.
We don't
You might
make
have a cell that you
of
use
this
twice in your design.
feature size
And
there.
did it really save you area or save you
Now,
speed? Probably
usually
not.
when the way I passed around there is chip
I mentioned
on board, so you can
my
actually
research
use
idea.
silicon.
My
where
first
the
master's
sizes
project that I
package,
proposed
the
was
board.
I'm not tell you when.
There are other ways of
the idea was to basically use those cells
You're probably familiar with
and I wrote some
1970s
stuff
stuff,
class,
which used to use basically these
I
like
could generate some
different
layouts.
pin
And the idea of this was
where you have a couple
doing
different
at the same time. As
ant
the idea
legs
of
go down, they
what
go into
we
the
call
board,
liquid
through the board, and so
Instead
on.
of pre-designing library, what you do is say,
Some
I'm
is
going to run
big
this
chips,
tool on
you
the
want
fly, and if I want to
connectivity
size
with
4.7
don't have very dense
converter.
connectivity.
Boom, I
If you
got
have a memory
it.
bus,
I can
there's
use
not much you can do with 14 pins.
Or if I want,
you want to send a
AO
32-bit address, you're
2221 gate.
So
Something
over
like
the
that.
years, there's been lots of different
No one ever
technologies.
did. No one used it. This would be perfectly efficient.
When I
Make
did my
gates
master's
use,
project, I'll show you in a minute.
The
I used a
problem
package
was,
like this. It was basically
we're
a
talking about
array.
in the class.
And here you can see
all
all
these
the
gates
pictures,
and
but
pre-characterized.
it still has kind of these
So it's not only
posts.
the time
They're not
design
just on
them,
the
but
perimeter,
it's characterized
they're also
the
kind of
performance in terms of power and
And there's
delay.
connections
And
to
to do that is very
to
slow.
those things.
And
It's all
if
made
you do a
with
liquid library, you either have to run
the
spikes,
14
which
pin
is
div is
impossible
actually made of
design,
plastic.
or you have to run
That's very
characterization in the
ceramic.
loop.
This one
And
here is
that's,
actually made of metal. This is an early Xilinx FPGA made in Taiwan.
So I actually, it was kind of my initial
all good
project
array, but instead of having
look
these
at
kind of
the
pins,
cell
it has
optionality
basically
of designs. So I would take a design,
that you can then solder.
and I would say, well, if I go through and make every cell the exact size
This
it wants,
type
how
of
much
connection
can I
is more
gain?
common because if you look at
And
density,
the ballpark
this
was
is much higher.
this is sponsored by
You have
DARPA,
much more
actually. They're
connectivity.
trying to make space
How many people
efficient
taken 120 in architecture
communication stuff for
you know,
planes.
memory is the bottleneck of almost
And
everything.
the question is, you can
You
make
want more
more
I/O,
efficient
more bandwidth for
with
memory.
time,
That's what pushes this.
and it wasn't really worth that. You do other things to
So you
save
see lots of
costs.
different
So the project
technologies.
didn't go very far.
Did anyone not see
They're
this?
gonna be good ideas, they're gonna be interesting ideas, but they're not always useful. Or not worth it. Because the added complexity in the design flow.
Yeah,
can
so
be
lots of
spent
different
doing
package types and
something
so on.
more worthwhile.
So this is actually my master's project.
You gain experience and you learn on that.
Which this was done in a 350.
Here's two
micron
specific
setup.
libraries
So
being
like
compared.
one generation, two generations
One on the
old
left
is
is
what
the
we're doing
Skywater
now.
library. This is actually a commercial library from
And
Skywater.
I have this just because I have all the pictures. They're
And
nice.
it was actually before it was Skywater, it was Cypress Semiconductor. I don't think I mentioned that before.
But
They
you
used
can see
it back
here,
in the 90s.
this design actually, you can see the package here, that went with that PGA we showed before.
For
You
like
can
a lot
see
of
this is all ceramic metal
display
pins.
things and
You
stuff
can
like
see
that.
these very
They didn't
fine
seem
bond
very
wires
well
here.
They still have
They're
their
like-
IP.
but basically like
It was a commercial
metal
library in
circuit.
130 nanometer.
And
They had
about
about
400
400 cells.
Here's a chip, and along
Pretty
the
big
lemma of
library.
this chip
A lot of
are these
libraries.
things here called
They have
pads.
45 different
that
flip-flop
connect to
types.
circuits,
This includes
like wires on
like
chips.
asynchronous
You just
set,
have a very fine
asynchronous
wire
set, synchronous set,
connected
synchronous
here
set.
to the printer of this package.
What else?
And then
Attached
internal
to
to the package,
is
it's a
where
wire
you have
that
what
you
scan in, because you may want to have input, but then accept a scan
So
when you're in
yeah, flip off
JTAG
the top of
mode.
this, you can see the bond wires and
Things
so
like
on.
that.
Now,
Has about 400 of
inside of
those
this,
440 are logic
this is
cells.
kinda cool. This
and it has
is basically
roughly
a
these
big
sizes,
SRAM.
1, 2, 4, 8. Now, in this case,
Here's a small
this shows a
SRAM.
size 0.
Here's actually a tiny
Sometimes it's called
ROM.
size L. And
This is
a
actually
special
two
case libraries
ADCs,
that
analog
we
to digital
talk about.
converters.
But
And
if
then
you
this
draw
kind of area
layouts,
here
it's an interesting thing.
is basically
If you draw
a
the layout. I've always drawn kind of a transistor like
And
this.
this was a
Oops,
chip that me and
There are a number
Part
they often don't put in there as a
people worked on
contact,
it,
right?
produced
They
an
draw
early
the
version that didn't work. My first job was testing it. It didn't work.
Those
And I
contacts
took
have
over
to
and worked with
they have to be so
this
far away
guy
from the
that
poly, they
designed
have to be
the
within the diffusion by so
And
much, they have to be an exact
it was
size.
intended to basically be a sensor
They have to be,
interface chip where the ADC had some
and
logic
those
also
are
to
designed
attach
now,
three
the
types of
distance
sensors.
between
A potentiometric sensor,
the
a
poly
passive
and this
sensor, or an
contact
environmental sensor.
actually
And
restricts
we
us
use
from
it
making
for
the
groundwater
fusion
detection and stuff.
shorter. If we actually measure the width of
analog to
this,
digital converter. So we take an
this
analog
dimension,
voltage
transistor
transistor,
is actually
bigger
bigger
than
than the
with a
14
digital signal.
So let's say we have
Yeah, so
130
one guy
nanometer.
did
This
some
is more
process analog
processing
stuff.
rate, 0.13.
This is just my master's
So
project.
if you look at the size of one
Really
transistor, I don't know what it is
tools,
exactly, but
but
it's something like 200.
And we had another guy working on it that did kind of the water monitor.
Make smaller transistors. Why don't I make a smaller transistor?
It was
Well, the
the
answer
answer
is,
this was
if I draw the
taken
layout,
out
the
with
layout
me
has to look
called
something like this.
They are now part of Texas Instruments. So, yeah. So it was basically a microcontroller, like an 8-bit microcontroller.
It looks like a dog
Think of it
bone.
like an
Dog bone
ST
kind of
micro thing you might use
why is
in
it a dog bone?
robotics classes.
Well, we have this
There
extra
are actually
rule.
two
I was
ADCs,
pointing out, I should point
different
out.
types of ADCs. One was higher
Between
precision, one was faster.
the poly
And
and the
then a couple
diffusion,
sensor
where it has to be
interfaces.
so far apart.
Yeah.
And so to shrink it down in that dimension, I have to spread it out and make it wider. So the wider
Oh, you're talking
transistor in
about
order to
like
make it smaller.
this stuff?
So I make it bigger to make it smaller, right? So most cases you might say,
The
well,
purple
let me
square
make
stuff is
it
ceramic.
this size, which will be
It's actually made
faster.
of solid ceramic.
And it's the same, it's less
Sorry,
area.
gloss over that. I mentioned
So
there's plastic.
in that case, this
ceramic
is usually
as
size
well.
1,
Why
which is
have
not really the
different
minimum.
heat? If there's a lot of computation you need to
Fix that.
Oops. We'll have some lectures on power later.
It's not that. This
It's
one
kind
would
of
be
ballpark.
130.
The plastic ones, you have to have less than 5 watts of power. I forget these things. Ceramic can go up to maybe. Actually, ceramic can go up to somewhere around.
Good question. Why do you want these
watts of
transistors?
power?
Well,
Then
we want
you
like
need to start not doing air cooling, start doing liquid cooling.
This one has bigger gate
We're seeing that in data
capacitance
centers now too.
than
And
that
all
one.
the power density.
So let's say I have a bunch of
That's
fans
the
that fan out of 16. It'd be more efficient to fan out
Yeah,
to
this is
16
a ceramic
degrees
one.
than
You don't
16
see this type of package too often anymore.
So
I'll
you
also
must
note
be
that this one, this microcontroller was actually designed to run with only 8 pins. Like I think it was power, ground, clock, a couple analog.
Yeah,
inputs
it
and
would
so
have
on.
more.
There are always other
That's
things.
a very good
I did that
observation.
for testability.
I'll tell you, this was an exam
I was
question.
like, I want to make sure I can
That's the
get
type of
this
exam
work.
question where
I
it's like
got
take the
a
ideas
bus
you just learned and apply it to
and
something new.
a bunch of
I had a
things.
dog bone transistor on an exam, and people would be like, "What is this?" And I talk about it, and I'm like, "Well, what's the capacitance of this?"
I can
Here's the
say
rules.
very easily
What
that
is
is 1 op amp.
Well, you can compute the area. How do you compute the area?
Yeah, this right here is an op amp.
Well, break it into two rectangles, right? Let me just take this over here
Yeah,
offline.
so you can see this one here is
we got
a
there?
there's a sigma delta op amp and then I forget the other type.
So just break it into two rectangles,
Yeah, right
sum up the area. What about the perimeter? Well, I want this perimeter.
Good question. Now, one of the
Same
bond
thing
wires.
applies
Now,
It's just
bond wires are one of the
give me
bigger
the
ways
constant.
of
I can
memorize
memorize the
There are different types of
constant.
bond wires. You can have the wedge
That's
bonds.
exactly what I mean by
where
applying
literally
this other thing.
you can have bond wire machines. There's a couple in Baskin. I was actually just talking with Nathan Ellis in ECE, and they have a
I
bond
can't
machine.
put that
Can I use it sometime? Possibly for the project in 127, that interposer project. I was kind of seeing what we can do to connect stuff on campus or what we have to pay
Yeah.
people.
Now, the other thing with these cell rows and heights is they're carefully designed with kind of the perimeter to make them
That's a good
DRC
question.
compatible.
Like, by the way,
these
DRC
DRC
rules
rules
are
are
random
complex,
questions. You have
right? And
thoughts.
that's why I'm doing the
What I'm
handout.
going to do at the end of every lecture is I have
That's the whole point of
time
libraries. You pre-design them so you don't
Like
have
literally,
to
so you have
yourself.
very
You
hot
just
topic questions, save them till the end.
packing.
Like,
That's
that's
what
what
it is. Kind of pack them into an area and then pack them together.
It depends.
Well, what they do is they make them placement friendly by adding essentially a placement boundary
Two
around
students before me started it
And
as a
what they do
class
then is
project
if you have
for
the
this
nacing
work
rule,
and did
it says,
that
oh,
AEC.
metal has to be so far away from
Essentially.
metal next to it.
They
They allocate
spent
half of that
about
space into one
semester
cell and half to the other. And
I
if all
spent
cells obey
basically
that, you
another
put any cell next to
semester
it.
debugging it, then another semester
So you have the same rule for poly
Keith, the guy who did
diffusion
the
for
AEC, spent
metal.
about 2
None of it
years.
can be within half a design rule
This
of
is
the
his PhD
perimeter.
thesis.
Unless you want to connect to the
The
next
memories I actually used
For example, the power of median ground
So those actually
will go
really
all the way
quick
to the end
design.
and
We
go
wrote a
to
company called
the next
Horizon,
cell. Because you
which is
want it
part
to
of
connect.
Card.
And it actually must
So
extend
they
so far
license
beyond
the
this placement boundary to ensure that
And I ended up the
Um,
Verilog analog took me,
in addition,
you
the
know,
end well. Usually, you don't make a cell with an end well that's only the PMOS
I worked on
transistors
this
in the
basically
cell.
for 2 years
The
in
entire
grad
row shares an end well,
And
and all those PMOS
yeah, so they all kind of
transistors
work
are
together. And then
otherwise, you have to ask
and then
the
actually
spacing
taking this
between
out
the end well
is
is actually
second
quite
year
large.
grad school to Germany.
So you have this
to the
huge
National
gap in
Science
there
Center,
every
spring
cell to
break
make
twice
sure
a week
they pass their
working with
working
engineers and using
So
their
instead,
licenses. Remember,
everything was
was
expensive, but it behaves the same.
We had some of the
Electrically
tools,
the
not
same.
these tools that they want you wanted, and also they had them set
And
up.
here we can kind of see this
So
example.
they were like, come here,
You turn
here's
on one of the
stuff.
layers in
So
SkyWater.
I
I turned
went
this
to
tan
the
layer.
tape out, and then they
Here, I
like-
turned it off.
That
I turned it off when I was viewing
like this is not
before,
production
but it goes
part.
to the
There are a lot of
midpoint
things
of the
in
supply rails
um,
all through here. It splits these
If
vias.
you go to something like
goes
Intel,
down the
they're
side
gonna
here,
have teams
and so
like
on, and it goes
100
through
engineers
here.
that spend like 3 to 4 years. And they're gonna have design teams that now start with like
It
5
goes through the middle of
people,
this.
up to a
You
couple
notice that
hundred,
there's a
then
via
down to
here.
their final test
There's
bed.
something else. There's
Over
this
that
via
lifetime,
between
they'll have
Li and
200
the
people
M1.
work on it.
But if we have another cell
maybe
down
the
here,
30,000
it's going to be flipped, and it's going to have this same shape there. Not only that, they also make these
On the
vias
back
on a grid,
or
so
just
they
this
all
here?
line up between the cells. And that means they actually make
No,
the
so I decided
widths,
where to put all
they're
the
not
blocks.
arbitrary,
That's
they're
gonna be
fixed
step called floor
on
planning.
grid size.
So
Every
every
side
side
size
has
is basically like
floor
half of
planning,
a cell.
placement,
Every cell is a
block tree
multiple of that
synthesis,
size.
routing,
Because it's basically one of these.
and
So that's
DRC
1, 2, 3,
I
4,
actually
5,
manually
6,
floor
7.
planned this. I decided,
why?
and for a number of reasons.
And that makes sure when you place this, then
I put this
you have board.
AEC
And
stuff
that
over
origin
the
is actually
because it's kind of very
this corner right
sensitive
here.
So I wanted to put things as far away from it as possible, especially things that switch. And
So it's in that corner because if I
what switches
place
a lot,
another cell
memory
next to it,
the
where do
memory
I put
buses
the
are kind
origin?
of over.
I put the cell next to it,
this
the origin
side,
to be right there at this point.
here,
So the next cell.
on this end, and they're very far from the ADC to prevent noise. And I
if I
all the
flip
memory
it,
buses
I
kind
go
of
like do the same origin,
area.
can I do the thing and say here, the
Hey,
orientation
this is a shared address space machine, so
the flip
they're
phone would have the
actually
same location too.
So that's the easiest way to put
That
them
makes it
together so
convenient.
they can easily be connected.
Literally, they're just packing.
Now, in
you
this
do that
area
correctly
here, this is
unless there's a
power
mistake in the library.
power and ground.
Which that's not a
power
library
ground,
frequently
and then
have
there's
some
rows
DRC
here
errors
for
from
standard cells, and you can't even see the wiring stuff.
because
It's way too small.
they don't actually try it.
That's all just
generally between all cells. So there might be some exception to the DRC rule that they run into that maybe they didn't think of.
So yeah, so that's
All right.
That's kind of what this is. So did I decide to put the S from here? Yes.
DRC, the design rule.
I knew it was
that's the thing that goes through
I
and checks all the
rules.
rules. I'll demo that if I can with the demo today. But
questions?
that's on homework 3.
Yeah.
Actually, I don't think I put a DRC problem on the homework because I'm not. Last year I had a homework where you basically give
PC
you
board
cells
design,
and errors and they fix it.
PC board design, you have ground
I had to go through and make sure
power
I
planes.
fixed it the right
You
way.
don't want to have ground
Great.
loops.
Yeah.
You generally don't have that in this type of
Yeah,
design.
the minimum spacing. So if you have a spacing of
When I talk about
0.5,
you
you
actually
have
can't,
0.25 between the boundary of the cell and any
metal
shape inside, and
There's
0.25
actually
between
rules
the
against
other
that.
Yeah,
because
the thing I highlighted in red.
What will end up happening is it'll peel off and
I'll show this
when
when I show
the
the
next
layer
layer
of cell
strong
libraries.
enough. So they don't do it in this case.
Yeah, and just to kind of further illustrate the alternating
instead
rows,
what they end up doing is using,
here is the midpoint
they
of
do
that
a bunch of crosshatch
supply rail,
lines close
and you
to
can see
the
here
ground
is an inverter with
It's a power
one of them
map.
flipped. So in this case, this is VDD here. This is
Yeah, you see
ground.
kind of the biggest, coarsest part
And
is
then
there.
this is VDD.
And under here, there's probably stripes, smaller stripes in the rows. There are smaller stripes in the rows
Now,
here.
remember, when you have these shapes for a mask, like those
They're just
contacts,
lower levels of metal.
if they overlap,
You
that just
only
means
see
I have that shape in my mask.
Like, that's
And
actually
it's
a
the
photograph
boring
of
of the
the
shapes.
shape, right?
If
That's actually
there's two
so
shapes
it's not like an
and two
electronic
cells
image
that are in the same
of
place, they add together, you have them in the mask. That's
Anyway,
why they have to
bonding-
perfectly line up.
This is falling out of
Otherwise,
fashion
what
for a couple
happens is
reasons.
perfectly line up.
One,
And let's say we had something like this.
You're kind of
Let's say I have
sewing
one contact like this, and the other one doesn't line up, and
There's
it's
actually
like this.
stress on this, and this can
What happens when I run
shear off
DRC?
and cause a
Well,
problem.
I have a rule for my physics that says they have to be exactly this size.
They can wear loose over time.
Now, oring those together
They're
is
rated
not
for
that
a
certain
certain
level
level
of
of
accuracy.
So they're super not reliable.
Right? So it's not just checking,
They're
all
usually
the
good enough for
rectangles,
most stuff, but
right
they will
side
fail at
is
some
the
point.
oring of all of those rectangles, the passing DRC.
The good part though is
So it kind of complicates
when
the
you're in the building, right? So
And that's why they do this width thing.
the
make sure those
percentage is
perfectly
they
line
mostly
up.
use this type, the ball bond type. This is only the less common type.
All
Just
right.
because it's a little more
Now,
distribution of the.
here's some other stuff.
stress,
This
so
is
it's a little more
important when you're a
reliable.
designer, and we talk about like that special pin layer where it just specifies where you want to connect to a cell.
Now,
This is
when you actually have the
related to
package,
how
this is something I
routing
do
happens to connect
as a grad
cells.
student. So you
And
get
if
your
you see
package,
here,
there's actually a
this is just the
data
LI
sheet
layer, and then the
that
red stuff
PGA
is where to
package
connect
uses
to
the
the
main
base of the
of
cell. I forget which cell is probably
And
an
what you
angle.
have, I had to go in there and I had a company do the bonding for me, and I had to basically make an image of here's my die,
Let me
what
get
connects to what.
So
you'll
you
have
have
these
these
kind of
images
there's
of
certain
certain
places
places
have
that are
good
good coordinate
coordinates
ways to connect to
in that
the
array,
pins, right?
which you can go through the package.
I could
Do I
technically
know
put
that this is going to be
this is this pin
red
from red.
left
I could have put it
corner
down over
here.
here, or I could put it over here in that middle. Anywhere would connect to it.
Why can't you utilize the corners?
But I put it right there.
Here.
And the reason I did it is because if I
so
want to go in
I
on a different
put it
layer,
around here.
normally we have the routing
There's
layers
actually
alternating.
there's a
One
metal
layer,
lane,
metal one will be
all the way around
horizontal,
the chip,
the next layer will be orthogonal
for
to that,
power,
vertical.
one for ground.
This way we keep, and then
Typically
L3 will be
for separate
horizontal.
power and
The reason we do that is
ground
because
for
make it
analog
L shape,
stuff, separate power and
use two
ground for
layers, you
IO
pack in more wires efficiently
because
because
those
they're
use
going
a
in the
lot
same
of
direction.
power. They're driving
They
these
don't allow you to go
wires
off
up, so
direction
you want a separate power.
unless there's very special
So
reasons.
these corners,
You see
all
what they
they
do
do
here
here
is
is,
they purposely pick these
wires
points
here,
so that these pins don't overlap, for example, in the horizontal
really
direction.
connect.
If I want to connect to this pin,
essentially a big
I can come from the
power.
left or the right,
This is
and there's no other pins here to block
and
it.
as well as some electrostatic.
Now this one up here, you notice
Horizontally,
horizontally,
up if you have
it's not aligned with that. You just draw the horizontal through all this.
prime transistor in your chip. So we'll have
If I draw a horizontal line,
so for
every
every
color
IO,
we
you
go
kind
high
of
layer
have what's called a pad. And
If I draw a horizontal line for blue here, it's here.
and so on.
This is on another track.
over here, there's no room for
This is on another track, and this is on another track.
Now
I could technically
do
connect
this.
all four of those
bond
pins
layers,
on just metal one.
I also had to
Right?
pick
That's
this
very
package
convenient,
because
very
there's
routable.
limited
It makes an
length.
easier
You can't
job. I don't have to go
bond
metal
metal longer than a certain amount.
Otherwise,
it becomes
if I didn't do that, what I have to do, I have to come in from the other direction, and this shows us coming in here.
Similarly,
on metal two,
this is using-
they also don't line up in that direction.
You have an angle. You have to have an angle such that you can make contact with this.
So it gives us the
metal
most
package
accessibility
as
to route to the
They
pin.
won't let you make too much of an angle.
This is the key where if you look at these libraries,
rules,
crappy libraries will not do this.
But anyway,
Because
I
the
sent an
designer
image like
did
this to the people,
Right?
and
But this is something you want to do, and
packaged
it's
in
very important.
Ireland, I believe.
Sometimes they might give you
So it was
multiple pins, but a
manufactured
lot of routers aren't smart enough to
in-
trade off.
I don't know where it was manufactured. It was manufactured somewhere. Then it was packaged in Ireland, then shipped back to us.
I actually think a lot, but the general idea, the general thing people do when they make a library, for whatever reason, they always just make these pins all in a row in the middle.
The other fun thing is
That's
that
like the worst thing, because
they
they have
do
no
measurements in
accessibility to
packages,
horizontal direction.
not
They
in
all have to be in vertical direction.
imperial units and not in metric, but like this other thing called mils.
Yeah, so that's why those are kind of staggering. That's also why you have that pin layer to say connect to this point with the router. Yeah.
It may be imperial, but it's not. I've never seen it before until I did packaging. 1,000th of an inch. Yeah.
You want cells
So
with
it's kind of
nice
nice
rows
round metric
so
is
the
number
spreading
of
out of the pins.
Right.
You want them spread out in each direction, actually.
There's actually been errors. I remember there was a NASA bug because of units.
So that you can do this.
If someone thinks
Like,
it's a
if I were to say-
it's actually 1,000th of an inch, that's
I
different.
come up with
but
a
same
case,
scale, right? Like roughly the same scale.
Like let's say we wanted to connect to this
Now,
middle thing
they
right here,
also showed
and I were to make
picture on
a
the
contact
first
or
lecture,
a pin for it like right here.
and so on. So instead of having these
Well, then I
wire
can't
bonds,
connect
you
on
can use
metal
wire
one,
bonds
both.
with three
I have to come from the right
Generally,
one,
they're
left
doing
to the
is
other.
they're very unreliable. So they're trying to replace them with a couple different things. One of the older ones is called C4, or Controlled Collapse Chip Connection. What is it? Well,
I
it's
see.
kind of like
So
when
you're saying, if I have two cells in a row,
it's kind of like
and I want to connect
the
from one cell to the
VGA
other.
packages on a board.
In
You put a bunch of solder balls, and
in
then
that
you
case, you have
have
to do some jogging
sucked into
maybe.
position.
Depends on the cell, because every cell will be a little
you can do this
different.
kind of design
I get
on
what
your
you're saying.
keyboard manually too. So they do
Let me
kind
draw
of
like a
similar
little
thing,
example up here.
with dies.
Let's say we have two cells that get placed next to each other.
So what you do is,
And let's say,
I talked about it a little bit last time.
we draw red. The pins for this one's here, and it's going to this pin over here.
This will
How
be
do I
the
connect to
top
that?
layer of a chip.
Well, you might be able to go through this
Either have
one,
connections to the
and then switch to
backside
metal 2 and go down like
the
that.
top metal layer, or going
Right.
through it with
But
through
you're still able to go metal 1 through out of this cell and into the other cell,
Now,
as long as it doesn't overlap
C4
any
is
other
one way
pins.
that uses basically a solder type material. They also use basically gold and kind of thermo pressing now to do finer pitch stuff. So
That's another good
kind
question.
of gold,
What
kind
are
of
these?
heat up, press it, and it will kind of
The inputs and outputs are not
This
always
C4
on
can
the same.
go down
Outputs are not always on
to
the right.
like, I don't know,
Inputs are
40
not
or
always
50
on the right.
micron
I
square.
don't know what this is in this case, but it
Whereas
could be
the
that middle one.
other thermal pressing method can
It
get down
depends
to
on
like a few micron square for
flip-flops,
make
especially
a lot
on
more
giant cells,
connections
where's the clock? I don't
from
know.
one die to another.
So
than
there's no
there's
guarantee. Also,
that's why
remember,
they do things
you
like
can flip
have
these cells
processors
horizontally
that
in the same
have
row or vertically to the other row.
When it goes
So
through
you have different
different
locations of where the pins are.
That's the best thing.
And that'll change where these locations are just by mirroring. Right? You can't rotate because obviously the rows are different directions, but you can flip horizontally, flip vertically, or both.
Now,
Yeah, good questions.
there's different types
In this
of
example, I went right on metal 1, then metal 2.
general
Maybe it'll make sense that I go
three IC
down
with
on metal 2
layers
and then
up.
right on metal 1.
You could
that might
theoretically
work
manufacture
better.
this in
But that's up to
one
the
plant
artist.
doing many layers, but what they'll often do is have kind of a big chip design. So this is all silicon with potentially transistors and so on.
I see what you're saying there.
And then
Yeah,
what,
you're
you have
placement.
one layer
What if I
up.
had the same
It's called
design?
a 2.5.
And instead I had, say, this cell.
It's not quite
let's say
3D,
above,
so you're only going one layer up. but it's still
like this,
not.
and then the other cell would be like this.
And so if you kind of omit these top rows here,
Then
that's
you can
going
check
to
with
with
yeah, the pedal too. That might happen. Yes.
So that's a good question. What's the most
Absolutely.
stacking?
The wire would be shorter. It'd be
This is
faster.
still
It'd
an
be
active
less.
area. But I think in industry, I think people are only doing
But there's always a trade-off,
right now.
and that's what the placers are going to try to do.
The problem,
But
again,
in this case,
is
that's a
similar
really short
to
wire.
stuff.
They're
You get
probably
too
both about
many
the same because
connections
that wire
and they're
capacitance isn't too much.
like lining it up, making
not
sure you
super
have 1,000
different.
connections
Yeah.
that they all connect. Testing it's super hard. In addition, if you have these dies separately, can you test
because
them
that
before
prevents you
you
from
put
getting
them
any of them out horizontal.
Because you don't want to put them all together and test it and be
It might
like,
be good for
oh,
vertically,
die
but
4
it's ended
or maybe die 1 didn't work.
The problem
You do
with
that.
horizontal.
You throw this whole thing out.
We did both. We spread it horizontally and vertically. So if you
Yes,
put them all in
and
a row,
then
you
you
finally
only
spread
spread
out
it right.
horizontally.
Once you start doing this, you can't get heat out. So the best way to get heat out of a die is actually through the
Yeah.
back side. So you have the active stuff
Now,
on the bottom and all the metal going
that's
up.
kind of the intro to cell library. That's why this homework, you look at cell libraries, you look at the height, you're measuring some transistors, you're kind of doing a
Whereas
lot
now
of
you have
observation
3 silicon
about cell
vias, you potentially have chips
You're
on each
corresponding
side. You
the
can't
logic
heat sink to this
of
die.
the transistor with
it just goes to its
greater
rated
than
status.
that.
So you get big hot spots.
Now this
in
is
the
just
middle
a
of the
schematic.
thing. Heat up and cause failures.
Now, sequential cells, I mentioned all of these.
That's why all these
are
designs,
matches.
they
There's
just
the
improve
flip-flops.
some stuff
So these are
to
level
allow them to
sensitive rather than edge sensitive. I don't think I mentioned those.
Now, the reason they
Oh,
stick
you'll
with
also
the
have
5
flip-flops, for example, with Q and
is
Q
they'll
bar.
frequently do
Or
something
just
like
some flip-flops only with Q.
maybe have
Because
one
Q
big
bar
die,
sometimes give you a
put the ones on
different
top, but you then have the back
Or you
sides
might
of
have
both
some
sides,
that are
top and the bottom.
positive
You can
clock or
extract heat
negative
out of both sides.
Right, so tons of
Then how you
different
connect to the bottom one, we
varieties.
maybe do some wire
And
bonding.
I didn't mention
on
the
the
enable
side
set
or
too. So
something.
even beyond the
So
async
they kind
sync
of
and
let you get heat out better.
I didn't say set here.
Yeah, so this is an area where a
lots
lot
of
of the
varieties.
most advanced chips are doing stuff like this.
Yeah.
So this is an actual.
The question
this
yes,
is the
is it all
backside
flip-flops having a
of
Q bar?
the.
It's a hard question
What
because
was this?
mostly you've seen
so
that in
chip
the
I
primary,
passed around,
secondary, or
it
master
was on
slave
board.
flip-flops.
This is the backside of that.
Dozens and dozens of ways to make flip-flops.
Okay.
That's actually a pretty
And
inefficient way.
what
of
this
doing
did was
usually they're done
you
with
may say,
some
oh
other
wait,
techniques. I've not surveyed
you know,
them,
like
but,
a chip like this has perimeter IOs.
in some of the cases you will
what
not
you
have
frequently
that.
do is in this case,
Or you, if you want to take that
also
version, you
frequently
turn around
IOs
buffer it, which might make the flip-flop
around
slower.
here.
And so the flip-flop will
This
have a better
is
set of
the
hold
design.
times
I had some
if you don't
loose
use
dies that were not on the
So
board.
the Q1 might be
You can see the
better.
perimeter IOs around there.
Because that- if you add a
what
buffer
they
that,
did
say,
is-
Q
this
bar,
happens
it would
to
slow
aid
down the internal
2.5
first
degree
latch.
stuff. Is they actually when you
Oh,
design the
why a
chip,
buffer?
we had
Because you
metal
may
one
want
to
to, you don't want to slow down
5
the
or
first
6
latch in a
different
primary, secondary
There's
flip-flop.
actually one
with
more
fan
metal.
out.
You don't use
Because if you add 16
the
fan out, then
it's
it
called a
makes the
redistribution layer.
So you got a buffer internal to the
You can
flip-flop.
see
Shield
the
that
traces
internal
of this, and
from
they're very thick, right?
Yeah, question.
Like right here. These are the RDL layers. Now, what we do in this case is it allowed us to basically
to have
reposition
different
where those
circuit
IOs are,
flip-flops?
and we put them into
Probably
these
not. You could, but I
areas
don't
like
think
this,
so.
which is called
Usually
area IO.
decided
And then you
for
put a solder bump here.
I'd say it
and then make a grid of this so that we can then
libraries
do
don't
chip to
deviate
board
that far
or
these
do a
days.
flip
It was kind of a
chip.
bigger thing in the 90s, 2000s when they were
Yep,
pushing
it's
frequency
kind of
a
like
lot.
let me
Now
now we
there's
redistribute
some
where the IOs
ranges
were to then
everything's like a
put
couple gigahertz,
to mount it
5
in
gigahertz.
Yes.
Like I know like Sun Microsystems and IBM, and they do all these different
Solder ball,
latch-based
same
designs.
thing.
And
Yeah,
like
you take a solder ball, you put it in
different
a
pulse
pad
flip-flops.
here, and then it becomes a
So
solder
instead of being edge triggered, it's basically a pulse
That's
on
kind
the
of
clock
colloquial
that causes the
term.
flip-flop to transition to capture. That was a flavor of the week for a while.
So I actually took this picture.
They complicate
I like
stuff. So again, it's like
AliExpress
you get
page,
benefit that's
right?
worse.
I bought a microscope for it was like $100.
It's managing
Let me see what I
stuff
can do. I got these tips. And I'm
So
taking
yeah, besides the
pictures.
flip-flops, you can get other complicated cells. Frequently,
decent
half adders,
picture.
full
That's
adders,
the
obviously make a lot of additions and subtractions.
There's a useful picture.
You might have a full adder with an inverted carry for kind of CSA adders, carry skip adders,
What
stuff
about
like
this?
that.
Yeah, so
you often will have
that's,
dedicated mux cells, usually
any
2 or
questions so
4
far? No
input.
questions, anything?
Tri-state cells, these are generally ones that you can effectively disconnect.
So
from
here's the actual
electrically. So you have a high
design.
impedance state.
So now these are
usually
not
you want-
photographs, but these are
looking at library,
electronic
you usually don't
designs
want
of
to
what's
use those
called
unless you have
GDS.
specific reasons.
GDS
Sometimes you want to know what's in the library to turn it
It's a
off.
term. It stands
Say,
for
ignore this.
graphic display systems.
Also, there are cells that are sometimes
Maybe
made just to be
graphic
delay
display or
signals.
GDS. It's actually
Like,
a
instead of
format
having an inverter, a
that's
buffer,
used in most
Skywire
chips.
library has
There's a newer one
What
called
would you want to use a delay
This
cell?
is the standard one.
Why
It's
would
from
you
the
make things
70s.
slower?
It was actually
Why
made
would you
in
want to make
earlier
things
chip design for basically plotters. And what it lets you do is all the
Timing
colors
control
are different layers.
Sometimes if a signal
Different
arrives too early, you capture
and
the
this gets
signal you
translated
didn't want. You want to capture the
layers
layers
used for manufacturing.
So if
you
you
have
have really
design,
fast task, you'll want
you
the
have different color, maybe
I'll talk about
metal
that
one,
during
metal two. Here you see the RDL layer over here is this purple. This is one layer that
Yes,
goes over the top of
optimization
this
tools will
die.
do that.
And,
But you may want to do it in a different way
This
because adding extra cells just to slow
was
stuff down is
part
a
of
bad
the Google series of products. Where for
consumes
2
power
years they
and
did 8
occupies
tapeouts.
area for
And there's a
having-
company called eFabless that
Yeah, and then I already mentioned
that
clock buffers. These are
basically
usually
made this
really
thing
big buffers
and let
for
people put their own
inverters
design
because
in
they're
this
balanced price fall.
Now you may say, okay, what is this?
again, you
stuff?
could
Well,
use these as
this is a
regular
RISC-V
inverter.
microcontroller with like a serial port, a
But
timer,
because they're
and
balanced price fall, they're a little
stuff
inefficient in terms of how much width they use.
These were 2 memories. These were actually my
Now,
designs. that got
there's a
used
couple
in
more
all of the
special
designs.
cells.
These were 2 SRAMs.
One is the
Actually,
cap cells.
they ended up
Now,
not using
remember
them
when
as
we
an
had
endpoint
NWEL,
because we weren't
I
sure if they
mentioned
worked.
this way
And
back
so
when I was talking about
designed
some
that,
of
I wanted to be sure that they
the
worked. So
kind of the
some of the
layout
techniques
techniques.
with flip-flops
That
too.
NWEL is going to be
Kind
connected
of
to the VDD, and if there's a P-well, it's going to be connected to ground.
So yeah, you put
How
it
do I
in
make
an
that
area, and then
Well, it's in with a
they did that
special
to then,
via that basically
flip it does that for us. But if I draw this, let's say I draw a substrate, and I have an end well like this. So this is high level stuff. We're going to talk more about stuff. So let's say that this is P, and this is N. This is meant to basically specify materials in the real world here, this N plus scale of the chip, connect to this N are happening. And then I put a V on top of this. That's what then it would be connected to the power rail, let's say. That's what this cell does. Very faintly, right? And then I might have, you saw at the bottom, if there's a P contact, I might have something similar. This is P type again. This is P plus. And I put a V here, connect this to ground. Let's take like a ground 4-minute break. Breathe. This is connected to VDD. So 240. So try not to go. I just have a special cell to do that for me. And basically, remember, all the rows share the same well, so I just put these every so often. And why do I do that? I'll talk about that when I talk about reliability. So I'm going to leave out why we do that. Now, we also have the I/O cells. I'm going to not go too much over these, but if you want to do inputs and outputs to your chip, it's usually with wire bonding, or it could be area I/O, but wire bonding has these cells that go around the perimeter, and they have a big pad here. This is usually the top level metal, and we also tell it to not put a final layer of oxide over it so that we can get to it and we can wire bond to their chip. And that is when you view chips, you can usually see that feature, because it's big enough that they can do the wire bond, right? Often pretty much with the naked eye. And then in this too, they usually have kind of wires that are your different power supplies. So you might have like VDD ground. You could have an analog VDD, an analog ground that's separate, or an IO VDD and IO ground, because you don't want to have that be with your analog or digital too. It might be a different voltage. And then you have corner cells, which basically take these VDDs and grounds and route them down to the other side, and then and so on. And then you see here, these things are basically all a bunch of vias connecting to different layers, because these horizontal things are often in say metal 1, 2, and 3, right? Because you want to basically have it be low resistance to the power supply. So you can see all the vias connecting up and down. Yeah. We can look. You can't really see here. So here's an IO ring from one of my chips that I made. You can't even see a logic cell in this. A logic cell would be about that big. I drew a thing over here. You can't see this.
ballpark. Like you can see these yellow wires are the top level wires. Actually, you can see the blue are the rows, right? So you can see roughly. Actually, I'm off by that. It's more like this. You can see kind of the rows. It might be, maybe it's kind of dithered too. Maybe you can't see all the rows. So, but yeah, that's kind of the scale in this technology. In other technologies, it's even more, right? One thing is this I/O pad ring doesn't scale down much with technology. Because you're connecting with the real world, and those connections are physical. They don't get smaller unless you start doing area I/O stuff. Remember I had right at the beginning,
I don't
flip
remember.
chip and stuff.
I wouldn't
Instead of having the pads around the perimeter, they're starting to put them right in the middle in the top layer, and you can flip the chip onto another one, make connections to the chip below. So that's a way that instead of having all the I/Os on the perimeter, you have them all over the entire area. You can have more bandwidth through the I/Os, but that's more expensive to assemble and so on. I want to get to the demo. Let me see. Is this stuff important? I'm going to skip. It'll be okay. It's on the next homework. So I'm going to continue this stuff on the next homework, or on the next lecture. It's not on this homework. What I want to do is flip over to the layout demo. Okay, really quick, we just have a 25 more minutes to have that fundamental kind of understanding, and then it gets more interesting.
So we had the kind of the overview stuff, and I want to talk a little bit about the photolithographic process. Now,
Otherwise, you
this
have
is the
basically
key of what makes the economics of manufacturing
that
successful.
when you get caught off guard.
And the TLDR of it is you make all of the chips on a wafer basically at the same time. Like you don't make a chip at a time. If you had to do things individually for a chip at a time, it would be too slow. So that's why all the processing uses this step. Now, the step itself is very similar to like t-shirt making or printing. Like you have a t-shirt that's like 3 or 4 colors. You basically have a stencil, you apply the ink, then you let it dry. You have another stencil, you apply the ink, you let it dry. Kind of like that. Except we add a little bit extra where we can do other steps like it'd be the equivalent of putting ink everywhere and then erase ink in certain spots. Because sometimes it's easier to put ink everywhere than not. But of course, it's not ink. These are different materials and so on. So what does this process look like? Well, first of all, we saw what a digital design is. We have the masks that are going to be this. Okay, this is make, so here we have Chrome. I recommend you clone the chip tutorials directory. And I did do an update. Some people asked me a few questions. Transparent. The first one was this homework you don't have to submit files with Git, so we put the tutorial for Git. But then it basically put a Chrome metal on it to make the searcher that some parts.
The second thing is how do you get to some of the technology files? Well, I include the technology files in the chip
mask that you have that electrical layer saying I want to wire here.
You end up having this directory. Put Chrome tech, and in here are all of those files you need for VRC, LBS, color schemes, and all that stuff.
Well, we use that in a machine that's called
you want this next
a
variable
machine. So we
to
line
point to the directory.
we shine light on one end, and it comes out the other end, depending on that,
and then it will look for the tech directory and Skyward 30, and you can select it and drop it down there.
Typically,
starting added for our other class.
192 nanometers is kind of the standard, but now they have something called extreme ultraviolet, which I forget the wavelength, but it's like.
So if you load it up and it doesn't point to this, it won't get the little design rules, and it will be not.
These extreme machines are global security research.
Now, another thing you want to do also is I updated this.
Only
it was
one
in
engine
the NG
manufactures them in the Netherlands,
which I cited here, but you don't really need to know it.
You hear about this? Oh, Taiwan got another EUV machine. Start going over. That's how critical these.
And at the beginning of this,
I think they have some in like Arizona now.
You can download them and let them offline.
But these are like
I updated this. Where if you want to get the library stuff,
what is the
you can use Python pip, and it's all this tool called Seal.
Right. Critical.
It used to be called.
The machine I use one here. I took a class in class.
There was a slight syntax difference though. You do seal and enable PK.
We use a machine that
hash.
This is
which version
but
you use.
you would basically mask in like a contact exposure.
You actually put your mask on the wafer, let the light go,
and then you pull it off and have time to rip off.
That's open source tools, right? You get bugs every time.
And then I mentioned I was in Germany.
If you run this, what that'll do is download a bunch of stuff.
Technological museum there, and they had our lithography
in this directory.
museum.
And if you run that enable command, it'll also make a link.
So
this guy
when it goes through there
is basically our technology.
so strange. I was using that last week in my class.
So there's 2 directories.
When the light shines through, there's actually material that gets put all over.
This includes stuff like K layout and
stuff fun on, and it's basically material
technology stuff for other
tools,
placement routing.
It's kind of
this includes the library.
I don't know what's in it. It's not really.
If I look in the
it gets
directory,
exposed to ultraviolet.
There's actually this K layout directory.
It will either harden and develop, or there's negative resist, which will not harden if it's.
But you can use this one, but I just use using one of the tutorial.
Now, the reason they use ultraviolet is that
another
material
thing here then is they have a replacement for
different
different
combinations.
Right, so it's and we talked about the different versions. So here's
that's not my area of expertise.
This is the naming scheme for this library. Skyward 30 kind of critical parts of IO libraries. That's those perimeter cells.
Now, once you have this, you have a pattern on this
polymer
material.
I'm calling it useful for dynamically making statistics, but we don't have that set up.
That's
This is the standard
for
cell
this.
SCHD.
Either you'll use that resist, or sometimes you'll
use the
basically
low
make another layer of the short cell first called a sacrificial, and then you basically do a step where you match the things that are not
cell high
right? Because develop will have protection from the acid that it gets exposed to.
I don't know what this one is.
It'll EUA.
This is SRAM parts.
This acid is typically either hydrochloric or hydrofluoric.
Some libraries are other versions of these
that
are not installed with Like there's also a
that will eat through your
low speed. Oh, it's actually a fast low leakage one. There's a medium speed.
Hydrochloric acid
Different variants, but that's the only one.
pretty nasty stuff.
I think they did that same bandwidth. These are big files. Now if you go into the standard cell,
we had a fab. Someone asked about our fab here down in the hall. Frequently,
autocomplete is your
friend, and you'd see people in bunny suits running down the
here,
outside corridor.
I started talking about file types.
The alarm would go
There's different file types in here. CDL is another version of Spice. You also use Spice directory.
It's a good idea not to
run ngSpice and use those. This is specifically for cadence tools. So anyways, you can do an language. They're basically the same. You do kind of a lot of cleaning. Again, with particles, with the materials, I was just going to talk about a simplified layout for the place and route tool. The library, this is all the timing power information.
I basically learned
these ones you won't really use for other layout formats.
There's a lot of cleaning.
And you have the Verilog.
There's a lot of weight
of yourselves.
And that's about what happens in a fab.
And then you can ignore text too.
But after you do this, you may etch.
So if you want to look at the GDS interface, go in here.
I'm kind of being confused, but sometimes the photoresist that's
the entire library. I'm going to load this up.
Protective. So what you would do beforehand is you put a material called oxide.
I was playing with the GF180.
It's stronger.
So remember my last
oxide to actually be your barrier.
It has this here.
So that's when you etch it.
So what I want to do is drop down, switch to Skyward 30. There.
Now the oxide I mentioned that I'll clarify. It's kind of like this photoresist is creating the
press this button
oxide. And then you use the oxide.
That's if you don't get the right layers over here on the right.
I'll talk about what this process is.
What is the cell loaded first?
And then you might remove no idea what photoresist, or you might remove that
flow
stencil
ISO buff source 16.
And then here you can add another layer of oxide with oxidation. You recoat and you repeat.
But over here you can see
changes
this
whole
thing with all the
different
cells.
changes is where you use the photoresist as your stencil or oxide.
You can.
But
I'm going to kind of right click. Show as new top.
What does that process?
Opens the main window. This is A2111.
Or first, what is the printing? Just to clarify the photography. EUV I have here is 13.5 nanometers.
Here's an example where they have multiple pins actually. That's a good example for that reason.
But here you generally have a system where you have an illuminator. This is your mask set, and this is what's called a reticle.
and then
you may
turn
have
the labels.
this is your mask. It may be
These
more
are
than
here.
one
There's
chip on
different
that. A lot of times it'll be like a 4x4 array.
These are all
of your chips.
D1.
So when you're talking about the
D1,
perimeter
D1,
of the wafer and why it's printed sometimes, well, sometimes you may have 4x4, so some of them have to be on the perimeter, but one of them's not.
What do you mean?
So you may want to print the perimeter.
So you're ANDing 2 cells and then you're ORing together
The limit,
3 other cells.
pretty much to a chip design, is the size of the
one-
one. So I'm pretty sure that
I don't know why it's
H200,
111.
that's 2 by 4 centimeters, is like pushing the size of what you can do in one of these. That's probably one chip per.
Yeah, presumably the router will be smart enough to try that. It depends on
This
the
is
router.
not the same
Some
size
routers
as your
will
actual
be
design.
better
Because obviously you can't make this chrome.
it's funny, you look through here and look at some of these other cells.
5 nanometers. If you can manufacture that, you can do a lot of stuff. So
This one,
is typically much larger.
So actually, look here. So this cell
than your actual
comes in the
design.
final number is size 1.
I have a
size
picture
2,
here
size
of the
4.
mask set
That's all
for
they
the
have.
wafer that I showed.
So let's open up the
Actually,
size
this may be a
4.
different run, but
I don't
over
know
here
if
we
they
had the
do-
40 designs or whatever. Maybe it wasn't exactly 40. You can see,
But this is
they're all
the
on here.
right?
And again, I
So
don't know which one was
now
on
what I
there.
can do, here's an example of stuff you have to do. There's a ruler here.
How
How
wide
wide
does the run mine was on? I don't recognize my chip because I had a pattern of 10
7 point,
SRAM macros in this area.
7.5 for that
So
one.
mine was not on there.
I think it's in microns.
But you can see there's,
I always mix that up.
was it 1,
And I
2,
switch over
3,
here, cut my
4,
ruler
5,
so you
6,
can see it's
7
half
by
width.
1, 2, 3,
4x
4,
1 is
5,
roughly twice
6.
as wide.
So 42. There were probably a couple in there that were not users. And
The
this
reason
is the
for
mask
that
that
is
you
probably
then put into that
this
machine.
example cell is output
It's
is not
literally
inverted,
the similar size.
So how do they size the cell?
Just
Well,
these
the
are
final
kind
thing
of
over here is probably an inverter. So they probably
This
do
is
a 4x inverter after.
Not
Instead of
huge,
one
like that big.
That's
And it
not
goes through basically an optical system that then takes the light,
But,
focuses it,
if we go
and then
back to this.
illuminates a reticle on this. And
Yeah,
you
you
kind
kind
of see this thing across
right
the
here.
wafer.
At least
It's
2 of
printed.
them, maybe 4.
Now, here's the case where if you do a lot of
likely a
things,
4x
and
inverter
print a little bit,
after
you're still
the
printing multiple chips at a time.
A2110 gate.
In our case, 42 chips at a time.
Sorry, A2110 I gate,
And then-
followed by inverter. So we loaded the
You can kind of calculate based on
A2110
this. A 7 by 7, 6 by 7 array of this, roughly that
That's one
corresponds
without
to
the inverter in the output.
I'm just eyeballing it, right?
And you also notice this one has a size
Basically,
0,
take the reticle,
which
kind of
let's see
step
if we
that
see
across.
that
That's how many exposures you're going to do with
maybe I'm
logic
lying
machine moving across this thing. It's really useful to see kind of perspective,
Yeah,
like
kind of
scale of all
like
these
here.
things.
Doesn't look like
Just
it's
kind of
actually
Then, then you print it.
There might
maybe
be
use
another
that.
reason that's.
Now, what are those steps? Well, one step I mentioned already is oxidation.
Yeah, I'm not sure.
What is oxidation?
Okay.
TLDR, it's rusting.
If you these are all
put
the
metal
same
outside, it'll develop rust. If you put paint
Yeah.
outside,
Oh, yeah,
or
right.
paint,
Like,
you get exposed to a lot of
you
light,
do
it gets
I'm
dim.
not gonna do it 'cause that's part of
That kind of dimming of that, making it dull, is oxidation. It means that the surface material
Don't worry
reacts
so much
with
about
air.
these. These are
and kind of
I don't
bonds
remember
and
some of them.
tarnishes
It's
it
kind of
in
like
some
I know you're ANDing 2 inputs.
Well,
you
in
have
our
like
case,
A1,
silicon
A2,
reacts with air, and
and
it
then
forms
you have
silicon
like
dioxide.
B, C, D, E. And
What is
these
silicon
goes
dioxide?
A1,
Well,
and A2, or B, or C, or D.
It's
Something
actually
like that.
electrically it's an insulation material.
Now, what is
It
for
does
example,
not,
B?
it does not
A2
conduct
B,
electricity.
well,
I mentioned silicon.
one
depending on
inverted
if it's
inverted.
doped or not, it can actually conduct
So
electricity.
ANDing
So adding
2,
oxygen makes
A1,
it not
A2, ANDed with B
And
inverted.
what we do is then we can either
So you got
this is
these
kind of a
inverted
cartoonish
inputs,
thing where you have a carrier.
That's why
all
they
of
break
these
down
different
to
wafers,
1, 1, because
you
you
put
could
these
have
into a
like
quartz
1,
tube.
1B.
That
That's
was
one
the
of
mass
these inverted, but the other two not.
But
So
so you
there's
put
tons
these
of
masks,
right? I'm not gonna get into
wafers into a quartz
the
tube.
rules
Basically
of
add
nature.
like you make it humid.
Yeah,
and
I
heat,
will start to talk about
and
that in the lecture. I'll talk
oxygen
about
in
the
the tube
lib file
reacts with
format.
the
The lib file format
the,
contains the
silicon
logic
performance.
function,
Now the temperature
timing,
and the
power
concentration
information.
of the oxygen in the tube
contains
can
the actual
change the
layout.
rate of the.
Then there's that other format, other file here I shared. This
The
left
founder
factory.
of Intel, Andy
That
Grove,
just contains
his
simplified
PhD
layouts.
thesis. So again, this is like the
and
not
you
too
use those
easy
for different parts of the design.
fairly
There's
restricted. His
different
PhD thesis was on the rate of oxidation
Now-
in semiconductors.
Okay,
That's why he went
that's
to
pretty much what I want to cover for the library thing.
Now, there's different reasons you make oxide.
Now, the other thing that's in
when we
here,
go through how to make the
we go
devices, sometimes
into-
you want to make a better oxide, which means
we're talking about this is the
thinner,
technology directory,
higher
it's not the
quality,
reference library directory.
and more
And here we
control.
have setups
You
for
may do this
K-layout.
slowly.
This is a digital simulator that is
Or
from
if you
the
just want to put
80s.
oxides
This is a
together between
digital
two metal
layout
layers, you
tool
want to be
from
thick and
There's an
there.
LVS
You may
tool
do it quicker.
from the 80s that these still get used for
you can control those variables to do this.
Even though K-layout can also do it, these are actually they're older
Now,
and
you
they're
pull
more
out, then you have oxidation
K-layout
layer,
getting
everything,
much
then you
better,
do
but
another
K-layout
processing
is
step
not-
to potentially
not
etch
super
that oxide layer.
It's not
Right? You pattern oxide over the whole thing.
right.
Now you put
It's
resist over it.
So they actually
It's
use
resist,
LVS
etch it,
for them.
it'll remove the oxide that's not covered with photoresist.
And
And
sometimes,
you
for
can
example,
with photoresist
you might
and leave the
made the
oxide
design
there.
rules for K-layout, forgot to check a rule, or made the check wrong. There's cases where that happens.
And
And here there's also
I'm not
NGSpice. This is the model files for simulation. So we're going to use NGSpice in our class.
It is humidity.
For the next homework. You look in here.
I'm not a chemist, so I'll say
specifically,
that.
there's a
I know this is
whole
a
bunch of
bit-
files in here, and they actually organize it incredibly
I'm
weird.
not 100%.
But you want to include one file, and that's in my.
this
I
basically
have the
describes
file
the side view
in
of
the
what I
example.
so you
If
start
we go
with
back
this
into the
on
chip
kind of
tutorials
upper
spice
left here.
directory.
It's all just bare
I have an
solid wafer.
example file.
You
You
go
can
through
see
and you
there's
do
this
the
top level
oxidation step,
file
which makes the pink.
here.
And then you
Sky1w.lib.lib.
that grows everywhere, 'cause you
That
put this stuff in,
includes
you can't control where it grows,
all
it
of
makes
these transistors
transistors
and
on
everything. So your PMOS models,
You-
NMOS models.
you then put a layer of
we have
photoresist over
high
everything.
voltage PMOS.
They
so
just
you're
spin the
seeing
wafer,
this
drop it in the middle, and it coats
the TT
layer.
refers to what
Then you go
call
through
the
the
corner.
mask
So this is a
process.
typical
Here you can
PMOS
see you have the
typical
mask with the chrome.
That's your common
The chrome here would
case.
block the
And
mask
that's now
from
we'll talk about
exposing
that
the
in a
photoresist.
The
Then
next
the
thing we
photoresist
include on line
it develops
3
turns
includes
green.
the spice model, and all of the light
Doesn't
doesn't
physically turn green.
So that
Then when you go over to this
A2221110I will have a
you
spice
basically
model.
either
for
put it in a a
and then we have
acid,
an example
and
test
it
here.
circulates it to make sure it kind of
You
makes
can
all
go through the
reaction happen
tutorial
wafers you
on
make.
Spice,
Or you can
as another
another
example. I made this tutorial. I feel like
uses gas.
there's no book that covers this. There's no.
Again, I'm not a physicist.
There's nothing really to open that is showing what you need to know as a designer. I highlight the important things. I've not used any different stuff in that tutorial.
Yes.
And now you might say, well, this is like a text interface.
How do you get to activate? It'll just be a chemical reaction. Think about like
My suggestion is
what's a
that
good example?
there are modern spice tools. They're all based on the old Berkeley spice.
I don't know, what do you
Berkeley made
do as a
spice in the
kid
80s.
with,
Everything is just an
adding
extension of
water
that. This format is the same for all of those tools
Yeah, bubbles,
in commercial use today. They might solve it faster, they might solve it more accurate, but they follow this.
trying to
There are
think of a
slight
good
differences,
example.
but not much. If you have a fancy GUI that you can click on buttons and run spice simulations, what does it do in the background?
There we go. That's a good
Dump this
analogy.
out to a
If you
file
treat a
and
wood
run
table,
spice,
half of it
and
has a lacquer on it, half of it doesn't.
I've run into
So
so many
something's wrong
problems
when it doesn't have a
where I
lacquer
want to
mixed
enable
in.
an option.
The
It's not
stain
my
will
thing.
react with the wood, and then
What I have to do, I have to go edit the file after it dumps it out, run spice, and then load my waveforms back.
I'm trying to think of other
Only way you can figure that out is by
So then if
actually
you do this,
so it may
you
seem
get rid of the
antiquated,
oxide
but
material,
it
and then you're left
is
with
incredibly
oxide.
useful, and it
Now,
honestly saves
depending on the step, sometimes you may want to use this
one
as
thing
a
that's not
mask
bad is
instead
doing
of
waveforms.
the
And I do recommend using something for
But sometimes you just want
NG
this
Spice has
as
something built in
an
that's called
insulator
Heat,
material.
but it works. Here's an example. This design, it runs it with a
Now,
voltage,
that etching,
1.8
whether
volts,
it's a
25
liquid
degrees
etch,
Celsius.
a wet etch, or
Here's a
a plasma
driving
etch,
inverter
it's
driving a
different.
fan out of 4.
A wet
The
etch,
tutorial will go
you
over
can
how
put
to
it in the
format
back,
these
you can
lines.
get it to work.
Each line.
Well, it's a chemical reaction. Chemical reactions go in all directions.
And the signals are basically the reactions.
Everything around it. So
I won't get
it's
into
going to go down, but then
right
start
down
going
here
sideways.
So it's a fan out.
It's going to happen.
Converter going to
it's
an
an isotropic
isotropic
in all directions
of size 1.
It'll actually form like number 1.
This
kind of a
declares the
trench that actually
power
goes
supply.
underneath.
By default, you don't have to declare ground. It's always declared. It's always called 0.
You generally don't want
That's a
that.
spice
Because when you did
convention.
this mask, you said,
And
oh, I
then
want something that's this
These
dimension.
things down here, this creates a
Now, if
pulse in
I
the
do an
input.
etch, and I have this
tutorial
little
talks
creep
about
underneath both
and
ends, I
briefly.
actually etch something that's not quite what I
I'll skip
intended
over
in the
this.
mask.
This says we're going to run a simulation
And
for
how much it
treating
undercuts actually depends
with
how long
the
you etched it, how concentrated the acid was.
Now, how they
So
differ is sometimes they'll
this
take
is
a
where
suggestion and
the
run it either
process
stop
engineer
early,
decides
it's done, or
what
run
can
it
tolerate
with less
here,
accuracy or
and
more
when you
accuracy.
etch.
That's the
Obviously,
difference
why
between
that's going to be cheaper. It's just a vat.
Then I just define these variables, and then here it does some
magic
magic
machines.
This is the other thing.
I don't remember how to describe it.
It's easier to do in the command line because you have to measure something by hand, like drawing a ruler in the waveform.
There might be some crazy.
This will measure, for example, a rising delay from the A
The
input
dry
to
plasma
the
etch
output.
basically is more of a.
This will measure the
It's based on charged
rising
particles essentially.
time.
Plasma,
This
where
is
you
actually the
charge
slope of
your
output,
die, and then
Z,
kind of the particles get attracted to it and shoot
So
away.
the delay and the slew of the low to high
Because it's
frequency.
shooting in a direction, it's
And right here is just some stuff we can make it run and quit out.
It'll do a sharp down cut. Now, but it's more
What does
expensive
it
to
look like
do,
when I
it's
run
slower
this?
to do, it's more complicated, and so you don't want to do that for everything. So that would get you
Again,
something like
you can
number
see
2 here,
Berkeley
which is
Tech,
more like what you want.
1985, Regents of California. Homegrown software, right?
Now, so now we can make
And since then,
oxides.
this guy in
Okay,
Europe was maintaining it since
make something that doesn't connect.
He's an old 80-year-old guy that
Well,
still goes to some
let's go back to the silicon. We have silicon, and we talked about dopants. P plus, P-type, N-type, we get
He's super
arsenic,
responsible.
boron,
If you run
and
it, you can't use it.
How do
You
we
can't
add that stuff after we've already made the wafer? That's implantation.
I don't know, maybe.
Implantation, we can
So
basically
here
do
we
it
can
in two
run,
ways as
ignore
well.
this,
A slow way
these
and a fast
warnings.
way. The slow
One
way is
thing,
called
if you actually,
diffusion,
I'm
and
gonna
diffusion is very,
this is an
no kind of
analog
what
device,
like
like
you put creamer in the
file
coffee,
is always a common.
you'll see creamer in the coffee at the start, but
I've run
eventually
into
all
so
the
many
coffee
people
will end up
when
in a
it's not
uniform
something useful
and
in
the
the
creamer will
first
disperse and diffuse everywhere.
Right, so if you look at that
it tends
example,
towards the lowest energy state, it tries to even out. Diffusion is the same thing.
I had,
Some of these
stars,
particles are
comic
going to
character,
surface and kind of
example,
diffuse in here,
analysis,
but they're limited based on how
When I
far
run
they move
Spice,
in the
load
silicon,
it
the
up.
solid material. But some of them will absorb.
It's loading. The reason it takes so long is it's loading all of those spice libraries, which includes diodes,
Yeah, okay,
photodiodes,
yeah, putting stuff on a shaved ice, it kind of gets absorbed in.
capacitor models, inductor models.
Now, that's kind of a slow process.
flash
It
memory
requires you to
device
heat it up.
models.
When you
So
heat it
that's
up,
why it's
the
slow.
silicon
This
is
is
a
my
little,
comment.
not melting, it absorbs more. Right? So
Well, then
you
you can
can
run
it going into the silicon by heating it up.
It ran a bunch of
You have
stuff.
to heat it up like 900 degrees
Interesting two
Celsius.
things.
Not
These
very
are your
hot.
a
It's
node is
very
basically a
hot.
wire. So
I
my
think
A input
silicon
Z,
melts at
these are
like
the
12
outputs of the 4 fan outs.
remember.
These are the initials
It's
below
below
melting
melting
point.
point.
The solves to figure out what initial voltage
And
it should be.
you'll have a
This is
concentration that's
basically
greatest at the surface and
nanovolts.
gets less concentrated
But it's
further you go,
numerical
and less
error.
likely
It's
that
not
it will
perfect.
diffuse in.
And then it ran, and here to output my
Ion
two
implantation is
measurements.
another
Here's the
step.
rise
This is where
delay.
you basically take your
where it
boron,
was
arsenic, whatever, and you shoot
triggered
it
at this time,
as
and
a
then it
particle
finished here,
after
and here's the
the
delay.
You
It's
can
triggered here,
control how
it
deep it
finished
goes
here,
and how
and
much
this
energy you shoot it.
So we can see that this is
The problem with that is it
yeah,
roughs
so
up the
that's
surface.
first out too.
So you end up like having targets, like a bunch of bullet holes through it in that top of that silicon, and that may not be good if that
Yeah,
ends up
that's
being
technically
part of your transistor. So you end up having to heat it
Yeah,
up.
you can type in the whole thing,
to
like,
fix
X1,
the damage,
blah,
kind
blah,
of
blah.
make that silicon become a lattice again. Remember that nice bonded
Yeah,
uniform thing.
kind
over
of.
here.
This is where they sometimes differ. So in HSpice, you have to put this. This would automatically run it and then quit.
Let's hold this question off because our entire next lecture is how do we do this.
I want to do
with
one thing
transistor.
first.
So next lecture is about making the devices. Yeah.
The last thing is you do want to view outputs. There's a plot command. You type plot AZ.
Yeah, one of the fundamental
Oh,
ways to
never
mention the
mind.
size of
Plot
things.
AZ.
If we're now talking,
waveform.
this is where
This
2
is
nanometers
your
for what can be a transistor, and we're trying to
But you can
make
see A is the red,
ions in there.
B is the
You're going to have like
the Z
2 or 3
signal is the blue.
ions.
You can see
Very
you're
hard
kind
to
of
That's one of the fundamental limits of manufacturing now. And these are called planar
All in here today,
devices.
so remember we also took time last time. I didn't go over the spice model, which maybe I'll do that in another class. So I can show you those parameters I talked about with the devices.
I'm not quite sure what they do, but it's not this same process. Yeah. So implantation. So this lets us basically take our silicon and either make it p-type or n-type, and we can control the density of it. Not only do we have p-type and n-type, but we also have p-plus type and p-minus type. This is just referring to how dense are the dopants. P-plus means there's a lot of boron or arsenic, and p-minus means there's a little bit, and p means there's medium amount. So they're very there's no fixed concentration, but it's a concentration essentially. Now there's another step that you can do also called deposition. This is basically how you can get either polysilicon, which polysilicon is a silicon, but it's not in a lattice like the